Good morning, the Honorable Mr. Chairman, ladies and gentlemen. Today, we gather here for the 14th Pacific Rim International Conference on Water-Jet Technology. I'm Huang Zhongwei from China University of Petroleum at Beijing, Vice President of this conference. And I will be serving as their host. First, on behalf of the organizing committee and the China Water-Jet Technology Society, I would like to extend our warm welcome and sincere gratitude to all of the professors, experts, and friends present today. Now, allow me the honor to introduce the distinguished guests joining us for today's opening ceremony. We are deeply honored to welcome Professor Li Gensheng, Chairman of this conference, member of Chinese Academy of Engineering, the Director of State K Lab of Petroleum Resources and Engineering, Professor Liu Benli from Anhui University of Science and Technology, being the pioneer of the high-pressure water-jet technology in China. Professor Liu is 88 years old this year. Now let's give a special applause for his attending. Professor Liu Tingcheng from University of Science and Technology, Beijing. He is the former vice chair of the Water-Jet Technology Society in China. Professor Lu Yiyu, Vice President of the Chongqing University. Professor Zhang Guangqing, Vice President of China University of Petroleum at Beijing. Professor Wang Jun from the University of New South Wales, Australia. Professor Peng Guoyi from the Nihon University, Japan. After my introduction, let's applaud together, okay? Professor Shinichi Warisawa from the Tokyo University, Japan. Professor Akihisa Kiraki from the Akita University, Japan. Professor Yuji Okita from the National Institute of Technology, Anna College, Japan. Professor Zhang Dongshu from Anhui University of Science and Technology. Professor Chen Zhengwen from National Machinery Industry Corporation at Hefei, China. Professor Liao Hualin from the China University of Petroleum, East China. Professor Lu Hua, Vice President of Nantong Costco Shipping Shipyard Corporation. Professor Zheng Jiyue from Northwestern Polytechnic University. At this moment, let's extend our warm applause to welcome all of them. Now I declare the 14th Pacific Rim International Conference on Water-Jet Technology officially open. First, let's welcome Professor Li Gensheng, the President of the conference, to deliver the opening speech. Welcome.
Dear distinguished guests, ladies and gentlemen, good morning. Today we meet here at Beijing to grandly host the 15th Pacific Rim International Conference on Water-Jet Technology. First of all, on behalf of the organizing committee, Warasabi, please here. On behalf of the organizing committee and the State Key Laboratory of Petroleum Resources and Engineering, I would like to extend my warmest welcome to all the distinguished experts, leaders, professors, and colleagues attending this conference. The Pacific Rim International Conference on Water Jet Technology, shortly for PRic2025, was jointly initiated by countries including China, Japan, United States, Canada, South Korea, Singapore, India, Australia, etc. It is a prestigious international event that integrates academic frontiers and technological exchange in this field. The conference is held every 2 or 3 years, and since its first successful events in Beijing in 1987, it has been hosted 13 times now, so this is the 14th in the countries such as Japan, Korea, South Korea, Singapore, Australia, India, Canada, China, etc. Over the past 38 years, the conference aims continuously protecting international collaboration and innovation development in water jet technology. China's research on this technology began in the 1970s, initially focused on the coal mining industry, with continuous breakthroughs and cross-disciplinary integrations in its applications have now expanded to a wide range of sectors, including petroleum, construction, transportation, chemical engineering, and machinery. It has also demonstrated great technological potential and broad application prospects in surface cleaning, precision mining, machining, rock breaking, and environmental protection. Nowadays, water jet technology is now contributing to the global pursuit of energy transition and sustainable development. For instance, by providing full life cycle green solutions from manufacturing to recycling for energy industries, such as wind and solar power. This represents not only the urgent scientific questions of our time, but also the core theme of this conference. Herein, with great reverence, we pay our highest tribute to the esteemed pioneers in this field, including Professor Chen Dazhong, Professor Shen Zhonghou, Professor Liao Zhenfang, Professor Cui Mosheng, Professor Xin Chen Liang, and Professor Liu Benli. We 特别高兴，88岁高龄的我们的老前辈刘本利先生，今天也精神矍铄地出现在我们的会场，跟我们一起来参加这个会议，让我们表示敬意。And Professor Chen Yufang in China, and also in Yahiru Sensei, Kobayashi Sensei, Hiroshi Sensei, Shimizu Sensei, and 王峰旦博士，Dr. 王峰旦 ，Dr. Summers，Dr. Michelle Hood, and Dr. Vijay, and all the experts and leaders of Waterjet Technology Committee. And also, 我们今天还非常荣幸的邀请到了历届的以刘廷成教授为代表的历届水射流专委会的领导和专家们，让我们表示敬意和欢迎。我们对国内外为水射流事业做出杰出贡献的老前辈和开创者致以崇高的敬意。这是我插了一段啊。This represents not only the urgent scientific question of our time, but also the core theme of this conference. Therefore, I sincerely invite all scientists and experts here to share your valuable insights so that together we can elevate development of water jet theory and technology to a new level. Finally, I wish the conference a complete success and every guest good health and fruitful discussions. Thank you.
Thank you, Professor Lee's wonderful speech. Next, let's warmly welcome Professor Zhang Guangqing, the Vice President of China University of Petroleum at Beijing, to have a welcoming speech. Welcome.
Distinguished experts, honored guests, ladies and gentlemen, good morning. In this golden autumn season, we are gathered here in Changping, Beijing, to commence the 14th Pacific Rim International Conference on Water Jet Technology. On behalf of China University Petroleum Beijing, I would like to extend my warm congratulations on the successful opening of this conference. My sincere welcome to all professors, experts, and industry colleagues who have traveled far from here, and my heart-left gratitude to friends from all sectors of society who have long cared for and supported the university's development. Water jet technology, seemingly simple, yet embodying immense power, has become a key driving force in the ongoing energy revolution, thanks to his distinctive advantage of being green, precise, and highly adaptable. We are delighted to see that in the traditional energy sector, high-pressure water jet technology has become a powerful tool for enhancing oil and gas production. Meanwhile, in the clean energy sector, water jet technology is also playing a remarkable role in the precision machining and processing of wind and solar energy equipment. This fully demonstrating its technological validity and broad potential. As a high-level research-oriented university distributed in the energy field, our university has always stood at the front of the energy science and technology innovation. We fully recognize that water jet technology serves as a crucial bridge linking the traditional and the new energy industries and connecting fundamental research with engineering applications. To this end, the university relies heavily on national key scientific research platforms such as the SETI Laboratory of Oil and Gas Resources and Engineering, and also the State Key Laboratory of Deep Geothermal Resource and Exploration. These platforms strongly support the in-depth research and interdisciplinary integration of water jet technology in areas including oil and gas drilling and production, geothermal development, and CCUS. We are committed to integrating fundamental theoretical research breakthrough from frontier technology and high-level talent cultivation, aiming to build an international innovation hub that spans the entire chain from theory to application. Finally, I would like to extend my best wishes for the great success of this conference. May all our distinguished guests enjoy good health, professional fulfillment, and continued excellence in your future work. Thank you again, once again for your participation and support.
Okay, thank you for your inspiring speech. Next, let's give a warm applause to welcome Professor Shinichi Watasawa from Tokyo University on behalf of Waterjet Technology Society of Japan to have a celebrating speech. Welcome.
Okay. Respected guests, ladies and gentlemen, good morning. It is a great honor to be invited to the beautiful Champaign here for the 14th Pacific Rim International Conference on Waterjet Technologies. First of all, I'd like to thank the Waterjet Technology Society of China, and then China University of Petroleum, Beijing, for their efforts to organize this conference. On the occasion of the 14th Pacific Rim International Conference on Waterjet Technology, on behalf of the Waterjet Technology Society of Japan and peers of Waterjet Technology in Japan, I'd like to express our warm congratulations on the opening of the conference and convey the sincere greetings and good wishes of our counterparts in the waterjet industry to all the delegates and guests present. At present, Waterjet Technology Society of Japan serves as a key platform for academic and industrial exchange. Currently, the Professor Go-Yi Pan here is the president of the society. It is steered by experts from leading universities and corporations. The society's activity spans diverse fields such as the precision machining of advanced materials, infrastructure cutting, demolition, the nuclear facility decommissioning, and medical application as well. Notable progress has been made in the development of intelligent cutting systems, ultra-high pressure precision machining, the cavitation theory, and the establishment of safety standards, which have significantly contributed to the advancement of waterjet technology in both fundamental research and practical implementation. It is my sincere hope that this conference will continue to promote exchanges and cooperation among Pacific Rim countries in the research of waterjet technologies. May the 14th Pacific Rim International Conference on Waterjet Technology be successful. Thank you very much.
Okay, thank you, Professor Watasawa, and thanks to the celebrations from Japan Waterjet Technology Society. Next, please return to your seat and for a group photo.
各位领导看下对你的3、2、1，微笑。好，再来一张，3、2、1。OK。
Okay, this concludes the first stage opening ceremony. Thank you very much. Now, next, let's move on to the presentation segment. The first stage will be co-chaired by Professor Shinichi Warisawa and Professor Liao Hualin. Please.
So the first session will be keynote speech, and then we will come to the Professor Owen-san, and then he will give us a special talk about the review of the high-pressure jet technology and the technology. Please start, Professor.
Okay, thank you. 这个为了节约时间呢，我就用英文的 PPT 用汉语来讲。这个尊敬的各位来宾，大家早上好。我呢就今天呢就代表咱们这个水射流协会呢做一个咱们中国的水射流理论和技术研究进展。这是根据我们调研的，还有这个给各位专家呢咨询以后，我们做了这么个片子。有可能不全面，有可能是挂一漏万。这个如果漏了，大家都包涵哈。这个里面呢，主要是有很多是我们团队的工作。这个现在我们这个团队呢，刚才像李老师介绍的，这个从我们沈老师那一代。这个钻井，李老师呢就开辟了这个水射流的晚井。05年以后呢，我们又开辟了一些新的方向。这个团队包括一些新的射流，像二氧化碳、超临界二氧化碳射流、液氮射流等等，这个一些新的应用。目前呢，就是在我们这个团队老师是19人，博士后6人。这个19人里边呢，有14位呢是教授，博士生。111，硕士生呢是228，基本上我们是360人左右的一个大的团队。今天呢主要给大家汇报这个5个方面的内容。这个背景呢就不用多说了，就是咱们水射流呢实际上是应用的非常广泛。你像刚才李老师也说了，这个矿业啊、切割呀、石油啊，这个等等很多行业。这个行业呢，现在是咱们的应用场景实际上是越来越广。咱们还是，我个人认为，咱们这个水射流技术发展还是很快的，特别是最近20年。这个发展呢，是50年代以来呢，咱们这个新型的射流理论，这个新型的流体介质、新型的喷嘴结构等等，咱们呢是都取得了这个长足的进步。下面呢会分布的给大家介绍。这个先介绍呢就是纯水、清水射流方面的这个咱们的一些进展。目前呢，咱们这个清水，咱们可以这个水泵呢，可以达到把水呢达到这个600兆帕，稳定的供热在600个兆帕。目前呢，实际上是中国正在研制1200兆帕的超高压泵，实际上是我们叫增压器。但这个喷嘴的一些结构，还有一些主要的呢，现在目前还是这个锥直型的。同时呢，我们这些年呢，这个出现了这个水射流诱导激光切割，这个待会儿有详细的介绍，还有这个 PIV 这个测高速的流场等等。这一块呢，现在是高压泵这一块，就是我们在620个兆帕的时候，现在我们国内呢就可以达到每分钟25升的排量， 这个呢主要是通过多个增压器串并联工作，单个增压器呢现在还达不到这么高的一个参数。现在呢我们测试的正在研制测试的这个泵，可以达到1200个兆帕，但是这个昨天跟吴总请教，也是咱们这个泵呢现在排量，但是高不了。我们现在排量呢大概每分钟半升，0.5升的这个排量。现在这个喷嘴的这个结构呢没有太大的这个革命性的变化，我们这个水射流呢主要还是以锥直型和这个流线型喷嘴为主。但这个材料我们这些年呢还是有长足的进步，从这个不锈钢到这个硬质合金到陶瓷，现在还有聚晶金刚石，一直到我们的蓝宝石、红宝石喷嘴，材料的耐磨性呢是越来越高。这是那个刚才提到的这个水射流呢诱导激光这一块呢，最近我看了一下咱们这个方面的文献呢集中发表，这个有很多，这块包括这个山东大学，咱们还有桂林电子科大，这个水射流呢诱导激光发展呢取得了长足的进步。它呢这有很多优点，比方说像它的切割精度可以到这个2微米，切槽的这个宽度呢现在可以降低到25个微米，就是咱们常规的这个水射流呢就是很难达到这么小的这个参数。对这个流场测试呢，现在我们目前基本上还是用的这个 PIV，就是这个 Particle Image Velocimetry 这种方法，它的这个基本原理，大家那个做水射流呢都比较清楚，咱们是用激光。但是现在呢，我们是05年、06年，我们进口了一套这个激光器以来呢，这个近20年也是 PIV 的技术也是取得了这个长足的进步。比方说现在这个2个激光脉冲。当时呢，20年前2个激光脉冲的时间间隔呢，我们认为已经很低了，是200纳秒。目前呢，可以到咱们国内呢，现在可以脉冲间隔到7个纳秒，而且呢 ，CMOS 它的这个速度呢，可以到这个2万帧，每秒钟2万帧的这个拍摄速度，已经远远超过了当初我们的这个1000帧。现在PIV 激光测速呢，这个是我们非接触测流场呢，可以说目前最有效的手段。它现在测速呢，可以理论上呢，非淹没状态下可以测到这个930米每秒，就是2维的状态；3维的呢，可以测到这个500米每秒，这是远远到咱们这个音速，空气中的声速。但这里面呢，在淹没状态下有一个问题呢，就是这个空化，就是淹没状态下这个咱们知道呢，这个水呢常压下超过14.7每秒流速，就会发生空化。所以呢，就是我们用 PIV 测淹没流场的时候，这个空化现象呢，对咱们这个流场测试干扰非常大，就是有的时候呢，容易把咱们的镜头给烧掉，这反光非常严重。这一块呢，目前还没有一个太好的解决办法。第3个呢是模料射流，这一块呢，从这个美国水射流他们的会议呢，也是做了很多。我今天呢也稍微多讲一些这个模料射流的。目前的模料射流就刚才实际上是根据咱们的这个泵的情况，咱们现在增压泵呢到400多个兆帕，咱们用后混呢也可以把这个模料射流呢，当然加到这个420兆帕。咱们航空加工模料射流呢，它的精度现在可以到0.05毫米。目前呢，现在我们出现了一些新的应用场景，比方说咱们山东大学做的这个 TBM 模料射流呢，辅助 TBM 绝境。还有一些应用场景，包括咱们的新能源。退役的这个风机叶片，咱们现在这个新能源汽车的电池，它的这个切割，还有我们石油行业，就是我们团队做的一些镜像井，还有一些煤矿，咱们重庆大学卢教授他们做的这个煤矿，瓦斯泄压、这个防突等等，这一块呢会给大家待会儿有详细的介绍。首先呢，这个模料射流切割呢，现在就连续的共杀这一块呢，实际上是我们安徽理工大学刘本利老师、张东树老师呢前面已经做的还是很早的，就是原来是用双模料罐把这个流体呢这个排量也是很高的，排量呢可以到2升每秒。但是呢，现在呢，就是我们经过这么些年的发展，这个咱们重庆呢又做了一些新的改进。在原来咱们安徽理工的基础上呢，现在这个压力呢可以到这个120个兆帕。原来我记得咱们安徽理工做的这个压力呢稍微低一些，不到100个兆帕。现在我们可以稳定到120个兆帕，排量呢可调，而且2个砂罐呢可以连续共杀，交替连续共杀。 这一块的这个超高压磨料射流呢，这个100兆帕以上的这一块呢，可以用到咱们那些石油的井口抢险切割，咱们废弃油气井，咱们海上的多层套管的废弃油的切割等等。对这种超高压的这个切割，现在这个控制方法，还有这个切割精度控制方法这一块呢，现在我们根据这个机械行业的发展，已经发展了这个5轴智能这个切割系统，磨料射流切割系统。这一块呢，主要是那个我们上海思迈，现在我们张世进老师还有郑吉岳老师他们做的这个，现在这个切割精度呢，现在可以到切割的50毫米厚的时候呢，可以到0.05个毫米。这些呢可以用到咱们航空领域的这种叶轮、这种叶片的这种切割，而且呢可以降低这个废料，降低1半以上。原来这个切割下来的废料呢太多，现在呢从这个对喷嘴的控制已经发展到6轴6自由度的控制喷嘴的形成。这个是主要是咱们山东大学李树才院士、刘斌教授他们团队呢发展的这个用磨料射流辅助 TBM 切割硬岩隧道。这一块呢，实际上是这个 TBM 切割呢，遇到花岗岩的时候非常麻烦，切割速度呢非常低。这一块现在咱们川藏铁路从雅安修建的这个川藏铁路。包括现在咱们 TBM 机呢打垂直井，他们要打800米的直井从山顶往下打，这个呢都遇到了非常大的这个难题。原来呢，实际上他们中交建到石油大学调研呢，想用液氮辅助这个 TBM， 一方面呢，这个液氮的这个供应成本，另一方面就是咱们岩石的这个导热系数太低，辅助这个破岩呢，它是一个损态的过程，不太理想。咱们李树才院士呢，用这个超高压的磨料射流，这个呢对咱们的泵、管线、喷嘴、阀门都要求呢是非常高，它需要长时间的这个连续工作。这样的就是完成以后呢，现在它的这个切割掘进速度呢可以提高这个30%以上。然后咱们新的应用场景就是磨料射流呢，这是用于这个绿色高效现场的这个切割退役的风机叶片。这一块的磨料射流的压力呢，这个达到380个兆帕，3个小时以内就可以完整的把一个叶片切割。现在咱们这个叶片呢实际上是长度也是越来越高，咱们的风机高度呢现在已经超过了260米，咱们的单个叶片长度170米，非常大的这个风机。这一块还有这个太阳能板一些退役的太阳能板切割，这一块呢主要是咱们这个常州，咱们江苏常州呢他们在做这一块，现在他们的这个这个处理能力呢，就是要把这个切成片儿，把咱们的这些有用的材料回收，每年呢可以处理这个常州那个公司每年可以处理2000吨的这个太阳能板。还有这个退役的咱们新能源汽车的这个电池，这一块呢，大概在2025年到2026年，咱们第一批的新能源汽车就是即将要退役它的电池，大概每年呢要产生300万吨左右的这种电池。这个废旧电池的处理是一个非常大的问题。这个目前呢，我们团队呢，李老师也提出来用水射流。用高压射流这一块呢，它切割呢相对比较安全，因为它有残余的这个电荷。用水射流呢，先给它切割完了以后，再用后续的化学方法提取锂和钴，咱们的这个稀有金属也算这个锂和钴呢，咱们国内每年进口还是很多。这个废旧电池处理这一块呢，现在我们正在尝试探索。今年呢，我们要接替一个国家自然基金的一个探索项目，就是这个。用高压射流处理废旧电池，下一步要立一个比较大的项目。这个在我们油气行业呢，就是用磨料射流呢，我们要钻这个镜像井眼。我们打了一个直井以后，我们希望打出像鱼骨井一样的、鱼翅井一样的这一块呢。现在我们技术基本上经过近20年的这个研发，已经 可以现场应用到现场应用的这个水平。第一步呢，现在这个微小的井眼里边，现在这个井的内径呢，通常在120毫米，120毫米左右。现在这个套管上，我们叫套管，开出一个窗口，完了以后呢，就是不起管柱，上提下放呢，就是叫它旋转90度，给这个喷射软管、喷磨料射流这个软管呢让出一个通道。完了以后呢，咱们这个我们就要现在不用这个胶管了，我们用的是半刚性的金属材质的合金管。这样呢，就是在这个井里面呢，可以打出多个这个井眼，形成这个像鱼刺、鱼骨一样的井眼的分支井。完了以后呢，这个提高这个油气产量。这个水平井里面呢，也可以应用。原来那些技术呢，在水平井里边，胶管的话不可以应用。现在用金属管可以打出这种像树根一样的、鱼刺一样的分支井眼，提高这个油气产量。这是我们下面做了一些实验，就是在套管上面，这是3成半的套管，外径呢139.7毫米，可以打出这个38毫米的一个窗口。这个时间呢大概20个兆帕，磨料射流它的沙比呢在6%的这个体积比，6分钟就可以开出一个38毫米的一个孔眼。在这个镜像井里面呢，我们用破岩，在地面呢用旋转射流呢破岩。现在不管是在这个花岗岩、灰岩，还是这个砂岩、煤岩上面，现在我们用20个兆帕的喷嘴加降，喷射出的这个孔眼直径都可以达到这个50毫米以上。目前呢，现在我们用的这个硬管，它的这个外径呢是1英寸，也就大概25.4毫米，就是这个孔眼呢50个毫米，完全可以让这个喷嘴和这个硬管通过。这是在这个现场应用以后呢，他们下了这个内窥镜看一下这个孔眼地层里面这个孔眼的形状。这个呢现在也是这个孔眼直径大概在50个毫米，排量呢这个转进速度每小时呢可以大约打这个3.6米。现在这个技术呢，可以有这个很多的这个应用场景，这个包括咱们的这个煤层气的开发，咱们地热资源的开发，还有这个水合物等等，还有二氧化碳，还有咱们这个抽油冷采等等。这个打这种鱼骨井呢，就是可以在非常多的场景下提高它的这个生产效率，提高产能等等。用磨料射流呢，就是这个在煤层里面提高这个渗透性，提高这个瓦斯的开采等等。这一块呢就是咱们实际上是很多学校哈，这一块咱们是重庆大学卢一玉教授那边，还有咱们河南理工魏建平教授、刘勇教授等等，他是很多咱们有很多教授都在做这方面的研究，就在井下在煤层里面呢用磨料射流喷射成孔。提高这个煤层的渗透性，进而呢提高这个瓦斯的产量。下面这个空化射流方面这一块呢，也是我们一个非常悠久的一个研究课题。这一块呢，现在是有一些这个喷嘴方面，现在我们这个空化喷嘴现在近些年呢有进步。然后呢，流体包括这个二氧化碳流体。它的这个空化现象，还有这个空化呢，这个用于咱们水质的处理这一块，主要是咱们武汉大学龙新平教授他们在做。还有这种多重空化的等等，下面呢会给大家一个详细，就是现在这个空化喷嘴方面呢。来提高它的这个空化效应。这个石油大学呢，现在我们提出来一个叫多重空化，提出一个喷嘴的一个多重空化结构，就是比单纯的氦木霍兹震荡腔要提高它的这个质极震荡空化效果。还有这个新的介质，二氧化碳，液态的二氧化碳呢，作为一个射流介质，产生形成这个空化射流这一块呢，也是我们武汉大学龙教授他们在尝试。这里面呢，二氧化碳一个含量，还有对它空化的一块的空化射流 也是我们武汉大学在做这个污水的处理，清除咱们用空化射流呢，空化效应，咱们知道空化效应呢，高温局部的微射流、高压射流，用于咱们水质的污水的处理，这一块主要也是咱们还有这种橡胶轮胎的这个处理，这也是咱们武汉大学在做。我们石油大学呢在做这个多重空化，用于这个流体，咱们油体井下的解堵，这一块呢，现在我们已经在井上开展了这个现场实验。这个油气井呢，就生产一段时间以后，这个孔眼呢会堵塞，影响这个油气的流动。这一块呢，我们是用多重空化喷嘴，这个把这些堵塞物呢给它解除以后，它的这个油气井的产量会有非常大的提高。这个用二氧化碳射流呢，就是开采这个水合物，这是也是我们学校呢是张一群教授这个提出来的，就是提高结合镜像井，用二氧化碳射流呢这个喷射镜像井，提高这个开发这个水合物这一块呢也是一个非常新的方向。最后呢，给大家这个汇报一下，就是我们最近发展起来的一些新型介质射流，就是我们前辈们呢基本上都是围绕这个清水射流。这些年呢，咱们这个流体的工作介质有了进一步的拓展。先给大家汇报一下这个液氮射流。这个液氮射流呢，实际上是也就最近把液氮打成高压形成射流，最近15年以内，咱们才发展起来，可以说。在一些特殊的工况。比方说军工、原子能等等一些保密场所，一些特殊的工况，他们呢现在就是有一些广会器皿、高压器皿，就是不能用目前已知的切割方法，包括激光线切割、机械切割方法等等，都容易引起这个危险的后果。他们就说这个只能用这个高压的液氮射流来切割。这一块呢，现在是我们跟这个他们合作呢，给他们做了一套装备，就是用液氮，但是用单纯的液氮呢，它的切割能力有限。我们是用液氮里边加石英砂。这个现在我们把液氮呢，已经可以达到60个兆帕的高压，到60个兆帕的液氮磨料射流就可以切割目前咱们特殊场合的一些很多广会器皿。这一块呢，现在我们已经做完了一套设备，就是用液氮磨料射流切割。现在这个切割速度呢，就是要切割4毫米，它的壁厚呢基本上在4毫米左右，4毫米到12个毫米。现在我们切割速度可以到每分钟这个5毫米，这个呢一定可以满足咱们特殊场合的需求。然后液氮，我们也是我们李老师带着我们这个团队呢，在做这个液氮。打上高压以后，液氮射流破碎一些高温的硬盐，特别是这个咱们现在发展这个地热，它的干热盐的主要盐性呢是花岗岩。这个高温以后，花岗岩的这个钻进速度会大幅的下降，对咱们钻头的破坏呢也很高。如果用这个零下196度的液氮和咱们200度以上的这个高温花岗岩，用它呢做这个流体介质破岩，辅助钻头破岩，这样呢可以大幅的提高钻进速度，而且呢每一种岩石实际上都有它一个临界温差，也就是这个超过这个临界温差以后，这个岩石呢在热应力的作用下会自动破碎。像这种花岗岩，它的这个临界温差差不多就在350度，超过350度温差，喷上去以后，我们现在这个喷的压力呢基本上都在20个兆帕左右。岩石呢这个高温以后会自动的破碎，提高这个钻进的效率。像这种把我们做的呢，把这个岩石呢花岗岩加到不同的温度，这个喷射的时候呢，在30个兆帕的作用下，岩石呢就直接就破碎了。还有这个液氮形成这个冰粒空气射流，这一块呢现在是我们已经做了一些新的尝试应用，就是用液氮雾化、水射流雾化形成冰粒，用高压空气呢1个兆帕左右的高压空气打出去，用于这个表面的清洗。这一块呢，后续有这个陆华教授呢会有一个详细的介绍，我就简单的给大家 介绍一下。这一块呢，这里边包括几个单元，就是一个呢制冰，就是怎么样制出我们需要的冰粒，大概在1毫米左右的这个冰粒。这一块呢，我们原来想的简单，原来想呢用冰块呢给它刨冰一样刨出来，但是不行，刨出来呢都是片状的这个颗粒。这样呢，我们用这个液氮的把液氮雾化，把这个水呢雾化，这样它两个呢降落过程中形成这个冰粒。完了以后呢，这个冰粒的输送也是问题，因为这个牵涉到有温差融化的问题，还有这个喷嘴结构等等。后边呢有一个简单的介绍，像这种喷嘴，现在呢目前我们还是用的咱们火箭领域方向的，他们用的这个拉瓦尔喷管，这个呢作为这个我们液氮冰粒空气射流的这个喷嘴，这一块非常好，它这个结构非常好，就在差不多在这个0.8个兆帕的压差下，这个拉瓦尔喷管呢就可以形成这个超音速的射流，就到350米以上，它这个流速呢是非常高的。目前我们已经完成了这个样机的制备，就是液氮冰粒空气射流，用于这个远洋货轮咱们内舱的清洗。清洗以后呢，要达到这个 SA 2.0级的标准，便于除锈除漆，便于下一步的重新漆装。这是我们和这个机器人咱们北航的，咱们做这个机器人带动咱们这个液氮磨料射流喷嘴，在这个船舶表面呢进行这个清洗、除漆、除锈。还可以呢用这个液氮冰粒射流呢用于这个岩石的破碎。这一块呢，像如果是在地面工况下，它的效果呢，在煤岩里边要远远的高于咱们的液氮磨料水射流，它的切割效率非常高。后边还有咱们的超临界，还有超临界射流。这个超临界二氧化碳射流呢，也是我们2000年初我们沈忠厚已故的沈忠厚先生、沈忠厚院士呢，提出来的，设计了一些这个二氧化碳注入的一些喷嘴，超临界射流、超临界二氧化碳射流，它的这个破岩等等。后边给大家一个简单的介绍。这个二氧化碳射流呢，用到这个 CCUS， 目前呢咱们这个因为环境问题嘛 ，CCUS 大家都很清楚。这一块呢，现在我们就是设计了不同结构的喷嘴，适用于咱们超临界二氧化碳喷射注入的。还有呢，咱们用于这个破岩的，咱们石油行业呢用超临界二氧化碳射流破岩形成孔眼，然后呢再进一步的压裂等，用这个超临界二氧化碳射流。用到这个压裂的时候呢，这个因为这个超临界碳呢，它的表面张力接近于0，可以形成一些微小的裂缝，就这个提高这个缝控体积，也就是提高这个超临界二氧化碳，它这个把地层压碎以后，它的这个体积比这个水射流呢，比这个水压裂呢以后呢，这个油气的泄流面积会有这个大幅的提高。这一块我们国内呢，现在还是5大呢，也做了这个超临界二氧化碳射流，用于这个废旧轮胎它的破碎，把这个轮胎橡胶呢，用于回收。这一块呢，后续会有这个详细的报告，给大家讲那种轮胎破碎方面的一些。最后呢，给大家介绍一下这个超临界水这一块的这个超临界水射流呢，我是19年到东京大学开会的时候呢，就是东京大学我没去。我在校园里边看见东京大学呢有一个专门的就 Singapore Critical Water， 它有一个实验室。目前呢，咱们国内郭烈锦院士就是西安交大的，他们也在做用于这个煤的这个气化制氢。这一块我们团队呢，在李老师的带领下呢，现在是我们是用于这个稠油降粘。咱们国内呢很多油田。原油呢非常粘稠，就超过5万个毫帕秒，甚至到80万毫帕秒，就跟固态一样。常温下呢，常温常压下就是沥青，流不动。现在呢，我们团队呢就在李老师的带领指导下，我们做了这个超临界水射流，这个对稠油降粘这一块呢，我记得前一段讨论过，这一块上它有2个作用，一个是物理作用，一个是化学作用。因为超临界水呢，它有这个超强的氧化能力， 一方面，高速的超临界水射流可以把稠油的分子链打断；再一个，氧化呢，形成更短的分子链，就可以把这个稠油降粘。这一块呢，特别是我们新疆的西北局、中石化西北局，他们稠油呢，非常粘稠，产量也高，急需这种稠油降粘的新技术。这是稠油降粘，然后呢，这个超临界水呢，用于这个气化，就是刚才说的这个西安交大的郭院士，他们现在呢在地下，把这个深部的煤层无法开采的，直接用超临界水，原位气化，形成这个制氢、制一氧化碳等等，也是一种非常有效的办法。这个呢，他们已经到了这个中试的地步。目前呢，他们计划每年每小时要生产这个5000方的这个氢，成本也很低。他们计划呢，每公斤的氢制的这个氢呢，要15块钱以内。最后呢，我还是想说呢，就是我们这个高压射流，无论是这个射流的介质，还是我们的这个应用场景，我们呢还有很大的发展空间，前景未来可期。好，谢谢大家，汇报结束。
Thank you so much, Professor Frank, for your excellent presentation reviewing the basic research and then application to the industry. Very, very interesting for all of us. Thank you very much. Let's give Professor Frank a warm round of applause again. Okay, so next please join me in welcoming Professor Jun Wang from the University of New South Wales. He will deliver a keynote speech entitled "The Water Jet as an Effective Machine Tool."
插上没反应。现在呢？啊，这个可以，是第一个。第一个。排练计时是吧？
Thank you very much for the introduction. It's also a great honor here today to share what we have been doing in the last decade. Today, my presentation is water jet as an effective machining tool. Partly from the New South Wales, still the emeritus professor there, but now partly at work in China. My presentation includes 4 parts. After a brief and short introduction, I will outline and summarize what we have been doing in the last decade, and also give some example to show that water jet is indeed an effective tool for the machining of advanced material. I will then move to discuss the work we have been doing on laser-assisted water jet machining, and finally conclusion. In manufacturing, I think we have to do something that as a task for engineers. One is we have to make it to meet the design specification. And secondly, we have to make sure that we make it economically to make sure the product is markedly viable. And for modern day precision manufacturing, and particularly for micro nano fabrications, we have to make it economically without process-induced damages. So some 25 years ago, it was claimed that damage-free microfabrication is one of the most cutting-edge technologies in the 21st century. We believe abrasive water jet can take some of the challenges. I think when we talk about water jet machining or cutting materials, we can certainly use a Chinese idiom, which is dripping water penetrates stone. But dripping water has very little energy. The material removal rate is far from what we required in manufacturing. So we increase the pressure of the water to form a water jet. So the water jet can cut some soft material and also for some other assistance. But still cannot cut engineering material because they're too hard and too strong. So what we do is, one is we add abrasive into the water to form abrasive water jet. So the abrasive water jet can virtually cut any materials. Another way is what we have been doing for more than 10 years, about 10 years now. Use laser to locally heat and soft the material, then use water jet to remove the material. We call it laser-assisted water jet. As President Huang just introduced, when we talk about water jet, abrasive jet, we include many ways. So water jet, air jet, or gas jet, etc. So there's also different ways to classify the process. We can, according to the fluid we use, according to the abrasive particle we use, according to the process we use, and also we all know that according to the way in which abrasive are mixed with water to classify the system, or we call it either slurry or suspension system, and the entrainment and injection system. I think the advantage and application is quite clear because almost all people here are expert in abrasive or water jet processing. I think for manufacturing of component, the very important characteristics of the water jet cutting is the cooled or no heat effect cutting process. Another one is the cutting force or stresses is very small, which not cause any discernible damage to the workpiece. Now I move to what we have been done in the last decade. The work we have been doing, I think we can classify in machining as metric scale machining. We use abrasive water jet and also use cryogenic ice jet. In the middle range, called meso or macro machining or nanoscale polishing, we use micro abrasive water jet and abrasive air jet. And to the nanometer scale or sub-micrometer scale or micrometer scale, we use laser-assisted water jet, even dual laser-assisted water jet. Our work actually cover a wide spectrum of the water jet cutting process from the early days of system design, cutting head design, and also optimization, the air-driven pump design, and also the slurry jet system. But all focus is very much on the front part. We look at the jet or abrasive flow and the impact characteristics. We look at the jet abrasive interaction with the workpiece. Then we look at how the material removed elementary, we call macro mechanism. We also look at how the curve or the cut is formed. With this understanding, we will be able to improve the system and also improve the process. We are also able to develop new technologies, new process, and also new equipment to realize this new process and technologies. In terms of jet or abrasive flow and the impact characteristics, our work including 2- and 3-phase flow. We also use ultrasonic vibration assistance. And in particular, we are looking at how the stagnation zone formed on the impact set affect the energy transfer from the jet to the workpiece, and also
the way to improve or reduce the stagnation formation. We also look at to change the property of the float in order to change the energy transform efficiency or the quality of the jet. Our work including CFD or computational simulation and also experimental study. We use PLV, as Professor Huang said. We also use laser Doppler anemometer, another experiment approach to look into the process. With this understanding, we'll be able to describe or model the abrasive velocity or dynamic pressure along and across water jet. Just to briefly outline, we have found in terms of the stagnation zone. And we found the stagnation only take effect in very close to the workpiece within 1 millimeter. And depending on other parameters, stagnation reduces the energy transferred to the target, to the workpiece, by average by 1/3, 33% in our study. And we have tried to use ultrasonic vibration to break or even eliminate the formation of the stagnation zone, but the outcome is not really what we expected. We still continue the work. In terms of abrasive material interaction and also the impact erosion, our work including look into the impact mechanics. We look at the forces, the stresses, the strain rate, the work hardening, the thermal softening, and also how the energy are changed or converted after impact. We look at the multi-scale or macro-scale impact erosion and also the macro-scale of how the curve is formed. Of course, the material we cover including brittle material and ceramics, semiconductor, glasses, and also ductile material in all metals. And in particular, we have done a lot of work on composite, metal matrix, polymer matrix, reaction-bonded silicon carbide, laminated material, and also amorphous. In our experiment, we have been able to achieve more than 700 meters per second impact speed for microparticles of less than 200 microns. With just an example, we found the erosion mechanism. For example, we use the ductile materials. And in the traditional definition, which we use something used for 50 or 60 years now, we call them cutting wear or deformation wear. We believe this definition only describes the mechanism on various surface, not the fundamentals. So after all study, we use fundamental element, and also discrete element method. We will be able to find the fundamental ways or underlying science, how the materials are removed pieces by pieces. So we have redefined the erosion mechanism for ductile materials. With this understanding, we are able to develop new technology, new process, and equipment. For example, we have looked into the turning process, including radial mode and offset mode turning process. We look at controlled depth milling and complex curved surface machining, surface polishing, and also micro machining. Now I use a couple of examples to show how we are doing for the advanced material machining. First, we'll look at the polymer-based composite. We know this material been increasing use, but it's very difficult to machine. The challenge for us, I think the most significant challenge is the elimination. We found that the elimination can take place in three major ways. One is in non-through cut. When we not cut through the material, there's tear off or delamination at the end of the curve. The second way that the delamination can take place is when the water jet cannot cut the fiber effectively, but pull the fiber down, then tear the material off. And the third way is the initial impact. So in abrasive water jet machining, we have to have very short, less than 1 second of pure water jet before we inject the abrasives in order to prevent nozzle clogging. So during that very short period of the pure water impact, the shock wave can cause the material surface to delaminate or pop up, delaminate. So once we understand, we also use computed tomograph to look at how to relate the delamination with the process condition. So with this understanding of the mechanism, we're able to optimize the parameter under the process to prevent the occurring of the delamination phenomena. We also use finite element method and CT study to look at the fundamental, the mechanism further into the fundamental of delamination process. We are also able to develop a window of parameter within which delamination will not take place. So after this understanding, we try to take a look at how we cut the carbon fiber reinforced polymer. And this is a piercing process. Each hole, we only use 0.7 seconds. So in one setup, we cut 216 holes. And after cut, we look at both sides and carefully on the final holes. We did not find any discernible delamination. So for relatively large holes, we use a cutting process, circular way of cutting. We can cut on different size, different diameter, but the large one is easy and the small one is difficult. You see, we cut 3, 4, 5, 6, even bigger ones. As I said, the bigger the easy for us. Again, we did not find any delamination. And we also use piercing and the cutting process for very thick carbon fiber reinforced polymer, up to 50 millimeter thick. And on the left-hand side, you can see this hole is a piercing from the piercing process, and the diameter is only about just over 2 millimeters. And there's no way that mechanical drilling can do it. On the right-hand side, there's a cutting bigger holes on 50 millimeter carbon fiber reinforced polymer, and you can see the quality is very good. When we compare with the traditional machining, we look at the cutting or edge trimming process and also hole machining. That's are the typical machining process we require for composite material machining in manufacturing. So what we found, the abrasive water jet is have a lot of advantage of the traditional machining process in hole machining or hole making, particularly on thin materials for large holes, for large depths to diameter ratio holes, and for almost all cutting of any thickness, any reasonable thickness of material, particularly for thin materials. And for less than 1 millimeter material, you have difficulty to mounting the material, the workpiece on the machine table. Now we look at the second example with machining of amorphous metal lamination. And what we're looking into is the iron basis amorphous alloys. And this material has superior soft magnetic properties. It's the most energy efficient core material for electrical machine that we know so far. It is the iron loss is only less than 10% than 10% of the silicon steel that we are using now. But this material is only manufactured in 20 to 30 micrometer thick ribbons. So when we make a course from this material, we have to make the lamination. The very thin ribbon with resin material, ribbon as bending material and also used as insulation. So the machining of this material is very difficult, partly because the composite material is including a large number of thin strip lamination, including very hard and strong metals and soft resin. In particular, this material is very sensitive to heat and stresses. So at around 400 degrees, that will be crystallized. It's not amorphous anymore. And the machining-induced stresses can deteriorate the magnetic soft material. So the superior property will be lost. There's considerable study around the world, including Iron Steel Institute in Beijing, Hitachi in Japan, Light Engineering, I don't know where now, but usually in Shenzhen, have done a lot of work to try to make amorphous metal into electrical machine cores. Either use the punching or shaping process, you use EDM or laser machining or even mechanical milling, the result is not as good as we hope. That's why this material is not used in commercial production of electrical motors, only used very limitedly for transformers. So the difficulty we have is, again, the delamination. That's a major issue. Another one is the control of the geometries, the shape geometry, and the shape consistency, which including the off-cut and undercut in the cutting front. So our research focus is to look sure that no delamination take place, no crystallization of the materials, to minimize or eliminate undercut or off-cut at the low portion of the cutting front. We try to increase the cutting depth and the efficiency, and also to improve the shape and the surface quality and the consistency. So after that, we use our work, have tried to produce some of the cores for electrical motors, and we found there is no crystallization take place on the material we cut. We work with Adelaide University in Australia, and they have a research team work on the motors to use our core material, the core we machined into electrical motors. And they found the energy conversion efficiency had been significantly increased. And the small motor, they found the energy conversion efficiency is more than 2% higher than the AE5 ultra premium efficiency standard. Now I look into move into the next part to look at the laser-assisted water jet machining. We also called laser water jet hybrid machining sometimes. Nowadays, laser has become very popular and increasing use in every part of the world. But we are now laser machining rely on melting and vaporization by heating. So this heating will be inevitably cause damage to the workpiece. I think somebody will say, yes, we do have super fast lasers which can realize cooled machining process. But we have to realize again that when you choose a material for cooled machining, you will have to compromise the productivity and the quality. So that's the problem here. Then we look at the abrasive water jet. It's very difficult or challenging to machine geometry in micrometer scales. But we are able to produce water jet in micrometer scales. But water jet, as I said before, have very limited capacity to cut engineered material because the material is too strong and too hard. So what we try to do is we use laser to soften the material, to heat and soften the material, then use water jet to remove laser softened material. So in this way, we are able to use water jet to machine engineered materials. So what we call mix water with fire. So the concept is to use a laser to locally heat and soft material and water jet to remove laser softened element materials. So sometimes we call that said laser water jet hybrid machining. And this process can be conducted use laser and water jet coaxial. That means laser go into the water jet. But this process will cause laser water jet significant interference. They will affect the quality of laser and reduce the laser energy. So what we try to do is the offset, as the middle diagram shows. They are separate. So we hope use this approach, the material can be removed at much below the melting temperature. Because we do not have to increase the material temperature into the melting temperature, so the low temperature, so that possibly require less laser and material interaction time. There is a potential for high material removal rate. And water jet at high pressure also have a better cooling action. So the feature that we can machine very much depend on the laser and the water jet, not really depend on the water jet anymore. The laser and the water jet can be independently chosen or selected for better material removal. We believe that's some of the advantage. Then we try to verify or validate what we propose. We use the work material including single crystalline silicon, single crystalline germanium. We use aluminum oxide, use PCD, use some semiconductor material including silicon nitride, silicon carbide, and gallium nitride. What we found is the material was indeed removed at a solid state below the melting temperature. They are very negligible thermal damage. But we do find the water in the process interfere with the laser and cause laser quality to decrease. So we then move to how to minimize this interference and at the same time to make sure that water jet can take effective impact and material removal. And that's some of the examples we machine use different process. On the left-hand side is the pure or dry laser cutting. You can see really the quality is really bad. So the next two columns is use laser-assisted water jet at different pressures. The people may ask me, how about the water jet? The water jet alone cannot take effective cut, so I have no picture for them. Then we use amorphous layer thickness as a criteria to assess the thermal damage or process-induced damage on the workpiece. What we found is for silicon, the amorphous layer thickness are less than 40 nanometers. In other words, it's really negligible thermal damage. For single crystalline germanium, we cannot even find any damage. Then we start to look at the heating and cooling process, how the materials are removed, and why the process did not induce any damage or any thermal damage to the workpiece. We use furnace difference method and build a model to look at. And we found we use the laser have a pulse width of 42 nanosecond, and off peak period, off pulse period is about 50 microsecond. What we found is during the pulse period, materials start to remove, but during the off pulse period, the material temperature will reduce back to the initial temperature or the water temperature. I think that is why that is no thermal damage. This diagram shows how the material temperature reduces with time during the process. In one word, for pulse laser, heat accumulation between pulses did not take place during this process. Then we look at the temperature, pressure, and the jet impact angle relationship. We found if we use 30 microparticle water pressure, we can remove silicon at more than 600 degrees below its melting temperature. So about 800 degrees that we can remove the material by water jet. So that's another reason we see why the process did not cause any damage to the workpiece. In conclusion, I think in the manufacturing area, the water jet will gain more wider use from the traditional cutting or cut-off process to machining and the micro-machining. But we do need to increase the machining quality to make sure the dimension and the quality or precision more controllable And that's possibly something we need to work on, either from fundamental research or applied research around this area. And the next one, we have to look to make sure that the energy conversion from the jet, from the pump to the jet to the workpiece is increased. At the moment, the efficiency quite low. Another one, we have to look at the macro process. We need to commercialize such equipment as soon as possible. When we look at the technology along, I think we have to look at how to radically improve technology, possibly develop a new generation of the technology. And in the last decade, we have been looking at how hybrid process, including, as I said, laser assisted. We use the hybrid with the electrochemical machining. There's other ways I think we can do in the future. Okay, thank you very much.
Thank you very much, Professor Wan. So, for a very wonderful talk. So, at the machining, we can expect the expansion of this technology to the machining tools. Thank you very much again. Now we will take 10 deep breaths. Please take a short rest and enjoy some refreshment. And then we kindly remind everyone to return to the conference hall by 10:40 so that we can continue the session on time. Thank you and see you.
meeting. So next, we will welcome Guo Yipeng from Nihon University, Japan. The title of his speech is Experimental Comparison of Abrasive Suspension and Ejection Jet, Flow Behavior and Cutting Performance. So Professor Pang, please.
Thank you much for your kind introduction. I'm very honored to be here to present our work. The title of my presentation is Experimental Comparison of Abrasive Suspension Jet and Injection Jets. This work is one part of joint work with Mr. Adachi and Katakura from Daiichi Kata Konyo Corporation. So I'm going to give my talk in the following order. First, research background, and then motivation and objectives, and experimental operators and methods, and the next experiment result and discussions, and finally summary. It's difficult.
应该是可以，这个
看不到。这是可以的，看不到是。看不到。这个那翻译可我是看这个方面At first, concerning research background, our work is mainly focused in cutting method for structure and construction sites. Conventionally, various cutting methods such as mechanical cutting and thermal cuttings are used in construction sites for remove and modify structural components. And also, wire saw cutting is often used, but all these methods may cause several environmental issues, and also, as shown here, vibration, noise, dust, and heat affected zone, etc. And in recent years, water jet cutting have increasingly adopted for its advantage in cooling cutting. And due to its property, it is suitable for operation in confined or hazardous work conditions. And it's easy for to be remote accessed and controlled. As for the water jet cutting, as we all know, water jet is usually used as pure water jet and abrasive water jet. Pure water jet, as shown here, for example, workers from Professor Summers and Professor Soyama, and it is mainly used for cleaning of mechanical products and surface improvement, pinning, etc. And for cutting of hard materials, abrasive water jet has been developed, and abrasive water jet is also classified into two categories: abrasive injection jet and abrasive suspension jet. As shown here, As shown here, abrasive injection jet is formed by injection abrasive into jet, and then air liquid particle three-phase flow will be formed. And the abrasive suspension jet is formed by propelling pre-mixed abrasive suspension. So the flow becomes particle liquid two-phase flow. It's quite different. The main application of abrasive water jets includes metal processing, cutting of stainless materials, etc., and air forces, shaping of blades, and also construction and mining, and automobiles, and electronics, and also recycling processing. All this application has well developed, but for Japan, we have a serious issue for the decommissioning of Fukushima Daiichi nuclear plants. So it is possible to apply water jet technology to the decommission of Fukushima Daiichi nuclear plants. And for this problem, we need to at first to research the following issues. For example, radiological safety and the remote operation, the equipment durability. All these key challenges are shown here: generation of radioactive liquid. All these may the issues for other research fields, and in our relation, the jet structure was jetting effection. For example, jet force, core length, turbulence, droplet, breakup, and cavity affect curve quality and depths. And also for underwater cutting performance, we need to treat about quick decline of jet ability and cavitation and abrasive dispersions. All these the last two issues is clearly related to the jet structure. And as for the concerning the performance of abrasive water jet, many works have been conducted, and the jet structure and the effect of nozzle geometry will be investigated. However, the detailed understanding of unsteady flow behavior and jet fluctuation of high-speed water jet is still unclear, and also detailed comparative data of abrasive suspension and abrasive injection and suspension jet is not still not divided. On this background, this work provide experimental comparison between abrasive injection jets and abrasive suspension jets under identical operating conditions by qualifying unsteady fluctuations of ASG and AIG by high-speed camera observation. And the second, evaluating cutting performance of abrasive suspension jet and abrasive injection jet and applicable pressure precious and transverse speed for engineering applications. And the third, clarifying the effect of operating parameters. Device for high-speed camera observation. Here, the equipment of suspension jet made by Maker A, and the camera is out here, and the light is just set opposite of the camera to give a uniform lighting. And all this picture, it take with synchronization observation is conducted under this condition as shown here. The injection pressure is up to 240 megapascal, and the lower is 90 megapascal. And the abrasive materials is Garrett 18H, and the image resolution is as shown here, and the frame rate is 40,000, and the shutter speed is 1/200,000. And this shows the arrangement of cutting tests, and the vector shows the direction of transverse and the transverse speed. And the operating parameters of cutting test as shown here, and all the nodal diameter is for abrasive suspension jet is about is 1 millimeters, and nodal inner diameter of for injection jet is 1.02 diameter, a little difference. And the main difference is that the concentration of abrasive materials for I'm sorry, it's reverse. For abrasive suspension is about 10%, and for abrasive injection is about 5%. It's quite different. And the operating pressure is just the same, and the standoff position for both abrasive water jet is also same. Set at the same conditions for the standoff of 10 times. And this figure shows two examples of okay. This is just observation of suspension jet, and it's the example for cutting test in air. And for in front of experiment, we have measured the abrasive concentration under different operating conditions, as shown here. For ASG and AIG, the measured abrasive concentration is shown here, about 10.8, and for the concentration generated by AIG system we used is about 400%, is much lower. And of course the variation, the area is about for ASG about 0.3 7%, and for AIJ about 1%. So here we can understand the effect of operation pressure is negligible. And the main difference is that for different systems, the concentration, the abrasive concentration is different. Here, concerning the experiment results, this figure shows the high-speed video camera, the motion of the here abrasive suspension jet and the Norway the abrasive injection jet. The nozzle diameter is also the same, but the width of jet is quite different. Here, to investigate the behavior of the jet flow, as shown on the right side, the timely arranged picture as shown here on the right. The up one is for abrasive suspension, and the lower is shown for abrasive injection jet. The injection varies much heavier, much slower, but the variation is much great. To measure the difference, the image analysis for these two figures has been made, and this figure shows the variation of grayscale just for the case of injection jet. On the injection pressure at 240 megapascal. And this figure shows the variation of dominator frequency under same condition. As shown here, the multiple, the dominator frequency of jet surface fluctuation varies from 0.2 to 1.8 kilohertz, and it demonstrates complex fluctuation with multi-frequency components. And this figure shows the distribution of dominator frequency for abrasive suspension jet, and the right one for abrasive injection jet. And shown here, the frequency, the dominator frequency for ASJ is much higher, but the frequency for AIJ is small. But the amplitude of fluctuation for ASJ is much great. So the dominant frequency of ASJs gradually decrease with increasing injection pressure from here 20 kilohertz to 13 kilohertz. And the dominant frequency of AIJ remains relatively consistent, typically with the range of 1 to 10 kilohertz. ASJ tends to exhibit higher frequency fluctuation, whereas the fluctuation amplitude in AIJ appears to be larger, accompanied by intensive abrasive scattering near the interface. And ASJ shows a degree of pressure-dependent periodicity, whereas AIJ demonstrates instructing instability arising from complex interior flow behavior. And this figure shows the average image of air flow and air flow. Just for we averaged 5,000 images together, and then investigated the shape of the jet. The right one shows the profile of the grayscale at the intersection of standard of distance x by d equal 10. And the upper one, the right upper one shows the profile of ASG, and the lower one is the profile of AIG. We may say the slope and the width of ASG and IIG is different. So varies from inside to outside. According to this profile, we defined the for jet flow. Shown here, the main one just shown by dj at the by the grayscale of 124 at the position, just shown here. I'm sorry, I can't show here. dj and the outer one, just the we may say here the lighter gray position, the big size of the jet flow is D1, just outside. And the main one is synthesized. We defined the size according to the width of the profile at the grayscale of 20 to 50. It's different with 14 banknotes. The night for the grayscale, we need to just a little, just shown here. This figure shows the variation of mean diameters of SG and LG along the stream direction. And the black one shows the water jet wise ejected by the injection pressure of 240 megapascal. $90 megapascal. According to this figure, we say that the wise the injection pressure. The mean diameter of AIG just shown in the right side is approximately twice that of ASG near the nozzle exit due to the difference in nozzle structure. And the mean diameter increases slightly with the injection pressure for both jet type. And ASGs exhibit rapid expansion within the range of x by d less than 10, followed by slow divergence. And AIG expands more linearly and maintain significant large diameter over the same distance. And at x by d equal 10, the mean diameter of ASG is about 20% than of AIGs. Moreover, AIG shows a wide error range greater than unsteadiness and abrasive skating due to the abrasive skating. And this figure shows the specimen cutted by abrasive jet. And this figure just in the middle shows the definition of curve dips. It may depend on the penetrated position, and the average dips is defined as shown by the dashed red line. And the curve-wise is shown by the figure on the right side, and the up one, B1, just the wise of curve at the upper surface, and B2 just shows the curve-wise on the bottom surface. And this shows the method to measure curve-wise. And so the curve dips, the cutting performance. The cutting performance is defined by H, the curve dips, and the curve-wise on the surface and bottom surface. And concerning the cutting performance, this figure shows the curve dips of ASG and AIG varies with injection pressure. The left side shows the blank one shows the result for ASG, and the blue one shows the result for AIG under the same working condition. And the right figure shows the effect of transverse speed on the same injection pressure. And we understand that the curve dips increase monotonously with increasing injection pressure of both jet types at a high pressure of P in equal 240 megapascal. The curve dips produced by ASGS is approximately twice that of AIGS. The curve dips declines monotonously with transverse speed. A sharp decrease occurs below VT equal 60 millimeters per minute. It suggests that a threshold beyond the which material removal becomes efficient threshold. This figure shows the comparison of for the effect of abrasive concentration. In our experiment, the abrasive concentration made by AIG system is not adjustable, but the concentration of abrasive made by ASG system is adjustable. So we adjust the concentration of abrasive for ASG just to the same level for AIG. And then this result shows compression. According to this result, we understand curve dips of both ASG and AIGS increase with injection pressure the same. The curve of ASGS is larger than that of AIGS under the same operating condition. Curve dips of ASGS increase with abrasive concentration. When concentration increase 2 times, the curve increase only about 30%. Just the right side for the cutting performance of ASG. Both ASG and different concentration, the the concentration is about twice times, but the curve depth is only about 30% increases. This figure shows a comparison of for the effect of transverse speed on the same working condition. So we understand the curve depth of AIG increase with the transverse speed monotonous, and the area of curve depth increase also with increase of transverse speed. As the speed increases, the errors of curve depth also increases. And finally, this result shows a comparison for the jet flow shape with the curve depth, and shows here the curve depth and the flow shape on the right side. The jet mean central diameter and the mean diameter and the outer diameter. Here, the result are shown in this figure. The red line, red solid line shows the variation of jet outer diameter, and the hollow circle of red one shows the jet central diameters, and the blue symbol shows the cutting, the result of cutting test for the jet, the top surface wise and bottom surface wise of curve. According to result, we understand that the curve-wise increase is monotonous with increase in injection pressure for both jet type. The curve-wise are related strongly with the central diameter D1 and increasing slightly with increased injection pressure. And finally, I would like to give a brief summation. Comparative investigation was carried out to evaluate the performance of ASG and AIG under identical operating conditions. The result shows that the mean diameter of AIG near the nozzle exit is approximately twice that of ASG's due to the difference in nozzle structure and jet generation mechanism. The mean diameter of both ASG and AIG increase slightly with increase in jet pressure. And ASG demonstrates a tendency of pressure indent fluctuation behavior, and dominant frequency decreasing from approximately 20 to 13 kilohertz. And the third, the cutting ability of ASG and AIG improves with increasing injection pressure. And the fourth, the curved width of ASG and AIG corresponds closely to the jet central diameter D1, confirming that the core region of jet dominant material is warm. The board of and unstable flow structure resulting in wide and less precise curve profile. Thank you very much for your kind attention.
Just now, Professor Pang gave the speech on how to improve the processing ability of ASG and AIG. So from the experimental research work, so he discussed the parameters from the concentration of abrasive and injection pressure and transverse speed. So give interesting and important fundamental research. So are there any questions? So also may I ask a question? So during your experimental research work, have you found any cavitation erosion or cavitation damage for AIG or ASG?
In this work, the cutting performance is mainly made in air circumference. So cavitation effect is not so important. We did not consider that.
Okay. Thank you. Any other questions? So, okay, thank you, Professor.
Thank you very much.
So next, I'd like to invite Professor Liu Yiyu from Chongqing University. The title of his keynote speech is Mechanism of Energy Transfer Enhancement in Abrasive Water Jet. You please.
Good morning, everyone. 尊敬的理工生的院士刘本利老师，尊敬的各位同仁，大家上午好。首先很感谢李院士、黄教授给一个机会，让我们介绍一下我们团队关于水射流研究方面的一些工作。我们团队几代人嘛，有5代人，主要是将高压水射流用于矿山方面的应用，这个做的比较多一些。今天我跟大家汇报的这个题目是模料射流能量传递的提升机理。这个原因是基于我们团队在这么几年的研究的过程当中进行了一个思考。以前我们做水射流往往是从应用角度做了大量的物理实验和现场实验，但真正的要解决射流本身和在应用不同的场景当中，从理论的方面能不能探索一条这个研究思路，这是我们以能量转换这个点，所以我们整个水射流，不管在水射流本身的研究，流体动力学的研究，还是在应用过程当中的研究，以能量转换为一个主线，那么把相关的一些众多的一些参数，怎么样把它建立起来，相应的一个逻辑联系。最重要的是在矿山上应用的时候，现在目前大家整个大的研究的背景是往智能化、无人化发展，怎么样建立一些大的利用我们现在这个人工智能的相关的理论和技术，将众多的一些参数怎么组织起来，形成我们人工智能的一些大模型，或者是为我们的无人控制来做一些理论的一些基础。这是我们整个团队这几年在做应用的过程当中进行了一个思考。那么想来想去，大家也回顾一下，真正的我们做模料射流以前都基于我们我的印象是我们读研究生的时候看的是陆大有教授写了一本2项流体动力学，那么特别是在模料射流涉及到水、流体和固体模料介质之间的，是从力学的角度进行分析思考，但是得了很多我们有创新性的理论的一些模型，但是在实际应用过程当中，这些模型要进行应用的时候，它很难的有解析解，你怎么办？所以后面的应用我们也查了大量的资料，我们的研究手段往往是这个大量的物理实验、数字模拟实验结合起来以后，这个花费了大量的这个时间精力，也购置了大量的设备。但真正的往这个大数据模型建立的过程当中，发现这些数据往往是比较分散的，很难的形成一个汇聚在一起，为今后的这个研究奠定基础。这是我们团队确实也思考了很久，找到了一个点，这个点行不行我们也不知道，但是经过这几年的探索来看，好像还有一定的进展。所以今天呢，利用这个机会向大家汇报一下我们团队在这方面的进展。 那么也结合我们正在承担的一个任务，刚才也汇报了，我们团队主要是将射流，不管是纯水射流还是磨料射流，用于煤矿、用于金属矿的高效开发。那么在开发过程当中，跟射流相关的就涉及到我们的流体和固体磨料之间的一个能量的一个传递的一个关系，也涉及到我们射流和岩石在破野的过程当中，它的一个能量的传递的一个关系。这些关系直接决定到我们射流本身的切割的能力和在现场应用的时候它破野的效率。这些都是怎么样来提升这些能力和效率，也是我们研究的一个出发点。正好结合我们承担了一个生地专项，其中有一部分的工作就是针对于我们金属矿山，特别是我们战略性矿产资源的开发，这些方面研究，当然也是我们能够列入到生地的重大专项。它也是国家的研究的急需，所以也是我们团队正在这几年主攻的一个工作。当然，这个工作在装备方面也和我们的陈正文老总一起的联合攻关，解决装备问题。我们主要是解决破野的一些相关的研究工作。那么这一个跟大家也简单的汇报一下，现在对于金属矿的开采，那么传统的采用是钻爆法。钻了孔，用炸药放炮进行这种方式，原因在什么地方？这个它的好处，它确实它的这一个从破野的效果来讲，肯定是比较能量效率是最高的。但是它最大的问题是，我们的稀有矿山，以金矿为例，金矿的它含量本身就比较低，然后用爆破一炮以后。矿山是金矿是采下来了，但是大量的废石也采下来了，所以是把大量的废石和矿石一起运到地面，然后磨碎，然后再分选，这个效率是极低的。第二个，爆破也带来其他的安全性的一些问题，所以现在目前从这安全的这个角度，很多金属矿山是对炸药的管控非常严格。那么很多金属矿山都在探索用机械法来进行采矿、进行破岩，但是金属矿大部分岩石非常坚硬，用刀具进行破碎难度是比较大的，刀具的磨损非常严重。就是刚才这个黄教授讲到的 TBM， 他们遇到硬野掘进的时候也是同样的问题。所以现在这个山东大学他们就是将这个后磨磨练射流与刀盘进行结合，进行提高整个掘进的效率，但是解决效果还是有限。那么我们团队就提出来了，用这个薄矿脉硬野水泥切割的高效连续智能化开采的。因为搞采矿的人都知道，煤矿它是实现了这个连续化开采，但金属矿它没有。现在目前整个矿山为了提高采矿的效率，都希望用连续化开采的方式，用机械破岩的方式来开采金属矿，但是难度很大。所以我们团队也结合这个对高压水射流研究的基础，我们也提出来了用这个磨料水射流来进行开采矿石，然后把废石停留在井下，不出井不出坑这样的一个方式，来提高我们整个金属矿开采的一个效率。那么在这个方面当中就涉及到了很多问题。整个水射流其实刚才各位专家讲的报告很精彩，但是在用磨料水射流在岩石切割开采的过程当中，它有特殊的要求。第一个要能够保证切得动，第二个要切得快，第三个还要切得深。我们平时搞后磨磨料射流， 搞我们建材加工的时候，它往往厚度就是这么厚一点，你切割都没多大问题。但是如果是我们在金属矿开采的过程当中，每一刀只能切这么厚一点，矿是没法用的，它至少要切一个循环1米、0.8米这样的一个循环，它才能够保证它的开采的效率。这样就整个对水射流提出了新的一些要求。所以我们这个包括大家对是这方面的专家，实际上大家对整个水射流，特别是磨练水射流切深走的时候，难度真的是很大的。我们也是花了大量的气力，也结合科技部的几个项目在研究，最后发现要提升它的切割深度和它的破裂能力，能量的传递这个部分恰恰是它短板。大家都和我们这个机械传动相比，能量传递的效率、流体传递的效率本身就很低。大家可以也看一下，就是我们整个水射流真正的把这个能量传递到有用功的这一个部分，占的比例只有20%左右，30%左右。这个就是导致我们用很大的功率去破岩的时候，发现整个一分析这个能量大部分是耗散掉了。包括我们后面的研究过程当中，实际上经过测试分析，发现一个什么样的现象？我们很多能量是在水传递给磨料的时候，把磨料破碎了。这个能量其实耗散量占比也非常高。所以整个在这个研究过程当中，不管是射流能量从水传递到我们的固体磨料，还是从磨料传递到破岩的岩石的过程当中，它整个能量的损耗非常大。这个部分也是我们如何来提升这样的一个有效的这个破岩的能量占比，这是我们研究的一个出发点。所以围绕这样的一个研究思路，所以我们根据它的新机理，就是磨料射流的能量的这个传递的一些相关因素，它的机理是什么样子，那么大概是有效的这个转化效率是多少，然后怎么样来提升它的这个有效率，这个都是我们这个研究的一个主攻方向。那么我们也是做了大量的这个实验测试，也利用比较这个先进的测试手段，对磨料射流的速度场、浓度场的测量，包括在测量过程当中，磨料粒径，那么从进口到喷嘴的出，它的磨料粒径的一些变化。这个也发现，在喷嘴的过程当中，其实磨料粒径是有一个破碎的这个程度是非常严重的。这个也是我们能量耗散的一个方面。这个我们做了喷嘴的前后磨料粒径的变化，这个规律进行了测量。实验这个结果也表明，在我们的理论分析的过程当中，往往忽略了磨料对流体的反作用力，这一方面都是在我们通过实验的测试，那就和理论的分析验证的时候发现这些问题。第二个，仅仅是物理测试会耗损大量的时间和精力，理论数值模拟不得不进行。所以怎么样对两项流或者多项流这样的这个数值模拟的模型和方法进行一个改革、一个改进，来充分的考虑磨料流体相互的作用以及浓度输运的一些精确的计算。这个我们也花了大量的精力，包括在计算的网格的划分。现在目前大家都有这个解析和未解析，这样都有各自的优点和弊端，但是最后是很难的在这个快速的计算过程当中，能够精确的描述整个流场的一些分布特性。这也是我们在这个数字计算方面花了一些精力进行解决这个问题。我们所以也建立了这个颗粒破碎的一些模型，能够比较准确的重现 实验过程当中的磨料颗粒的破碎的情况，也明确了固体磨料破碎发生的区域以及相关的主控的一些因素是哪一些。我们也解决了传统的这种算法它的发散的问题，也发现了在球面的两项流动的阶段，粒子碰撞时间小于持续时间，粒子间的碰撞主导粒子的运动。这个就是特别是在整个的运动过程当中，固体磨料粒子之间的相互碰撞，对整个这个磨料的加速的机理影响也比较大。也提出了磨料群的动能的密度和磨料能量的输运的效率的计算模型，也建立了考虑磨料分布的前后磨料射流的效能的评估这个模型，来突破了仅用磨料速度衡量射流能量的一个限制。因为我们从这个流体动力学考虑主要因素还是以速度来作为衡量的一个指标，但这个指标确实不能客观的全面的反映这个整个射流的传输的一个机理。我们同时也对它的内流场，包括能量密度，在喷嘴的内部它的一个分布的一个状态一个规律。有时间关系我就不能展开了，因为这个我们有相关的论文都已经发表出来了，大家如果是感兴趣也可以查一查我们这个团队写的一些文章，这些文章都是在主要是在国际期刊上发表的，大家可以去看一看这一些。这是这个。同时我们也获取了磨料破碎前后的能量的变化的定量的一个数据。这个得到的结论，特别是下面的一句话，那么由于破碎以后磨料的表面积的增加，平均破碎磨料能量耗散是超过了90%。这个是这个具体的数据可能还值得一个进一步的深入的探讨，但是也反映了它这一个能量的耗散是非常大的。另外一个，我们也是大家知道要提高射流的能力，那么压力、流量、磨料的粒径、磨料的密度、磨料的浓度，这些参数特别多。那么怎么样能够把这些多因素的参数能够梳理出来以后，成为一个比较清晰的一个研究的思路？这个也是做了一些大量的探讨。我们也从射流的压力、磨料的浓度、粒径等等这些方面，对它的能量的这个传递的效率进行了一个分析。那么在磨料和这个破野的过程当中的能量传递的一些研究，我们也搭建了这些实验的平台，也动态捕捉了材料的破坏过程和动态应力的一些变化。现在这些测试的这个平台获取了磨流冲击作用下岩石的时空响应。因为刚才也汇报了，实际上刚才这个彭教授讲的，看到那个图片，切割金属材料这一个楔形的这个倒三角形的这个形状确实很明显，但是往深部岩石往深部延伸以后，它形态发生了很大的变化。我们切割的花岗石现在达到了这个0.8米，那么剖开我们岩石的这个样品以后，发现它比金属材料切工的不太一样，差别是很大的。另外一个也提出了这一个比较新的材料冲击响应的一个时候解耦的一个策略。那么开发了这些一些算法，这个有点重叠了，大家可能看不太清楚。通过我们这一个数据模拟和数据的处理结合起来以后，能够尽可能的揭示在水射流破碎岩石的过程当中，它的相关的一些响应的特征。那么我们也建立了这一个磨料射流破岩的数字模型，这个适用于射流冲击作用下 高应变率的岩石的损伤，这个也是我们后面用水射流去智能化切割硬岩打下这种基础。我们现在的追寻目标，其实我们实验室的样机已经研发出来了。我们整个的这个射流的发散装置，到机器人的执行机构，到整个喷嘴的以及我们的控制的系统，基本上研发出来了。有可能正在联系今年在2025年在金属矿现场进行做一个市场研发市场的应用，能够验证一下我们这些研究的一些成果。这个也对这个整个水射流破碎硬岩、花岗岩这种过程进行了一个理论的一个数字一个分析的一个过程，都已经能够通过数字化来展现我们整个的一个破岩的过程。这个也明确了整个能量传递和破坏的一个形式。也明确了这个水泄与沙电的一个效应对能量传递和岩石破坏的影响的机理。这个以前我们讲水泄的作用，实际上我们磨料以后，磨料在里面也有沙电的一个效应。另外一个就是也对射流的一些主要参数，对我们整个岩石破碎过程当中它的一些影响的一些规律，包括对岩石应力分布的一些影响的一些规律。因为我们整个水射流破岩的和金属切割还不太一样，它整个的机理是不一样的。实际上我们现在目前对水射流，大家以前看到了我们崔默胜包括刘本利老师以前写的那些书，实际上对纯水射流、磨料射流的破岩机理实际上做了一些很好深入的一些研究。但是我们在基础上发现了它的这个岩石破碎的机理还有很多一些特殊的一些情况，特别是跟我们整个破碎过程当中应力的重新分布影响也是比较大的。那么如何来提升？所以结合我们前面的数字模拟和实验的研究，我们也建立了前混合磨料射流。这个可能我们国内的大家都知道前混合式的，但是可能国外的一些朋友可能还不知道前混合。前混合就是刚才我们彭院士讲到的，就是 abrasive suspensive jet 叫前混合射流，然后后混合射流英文叫 abrasive injection jet 是这样的一个概念。所以这个呢是我们也建立了这个前混合磨料射流能量传递用于破岩的一个计算的模型。那么也构建了磨料射流从形成到破岩能量的传递的这个模型。这个模型为我们后面构建射流在破岩深度的预测。这个跟大家汇报了，在我们用水射流去开采金属矿的时候，这个深度是很关键的一个因素。那么怎么样根据不同的岩石的类型，能够比较准确的预测我在不同的这个水泥参数的作用下，它的切割的深度是多少？为我们整个在智能化采矿或者是整个采矿工艺的设计是至关重要的。所以这个我们也花了一定气力开发了这样的一个模型，在我们前期的模型的基础上开发了这样的一个预测的一个软件，然后把相关的参数输进去以后，就能够比较准确的预计我这个切割的深度是多少，为整个采矿的工艺设计奠定好的基础，也为后面的这个无人化和智能化开发也奠定基础。那么我们也进行了一个实际的测试，根据软件预测的结果和我们在实验室切割花岗岩的这样的一个结果进行对比，发现整个的效果预测效果还是不错的。这个是整个的情况。那么后面，那么结论是，实际上我们今后开展的工作是要考虑相变和磨料的相互作用， 建立考虑企业项间的滑移的六项耦合的模料射流开源数字的模拟模型，并建立在多模态的大语言模型为射流流场演化以及切割破碎过程中建立的实时的数字的镜像，服务于多场景射流、绝境、开采等条件下面的性能的预测和提升。这是我们整个实验室的一个工作。那么这一些现阶段做的一些工作，为后面的这个我们认为确实也奠定了一些取得了一定的进展。我们也希望在今年能够在现场能够对我们的这个前面的工作进行一个验证，希望也能够为我们这个金属矿的高效开发、智能化开发打下一定的基础，特别是对我们射流的推广应用做出一定的努力。我的汇报就是这些，谢谢大家。
Just now, Professor Lu gave the speech on his research report on deep mining, especially from the point of view how to improve the energy transfer with the abrasive water jet. So it's very important work for establishment of numerical simulation and interaction of abrasive and rock. Also establish important method for intelligent prediction of energy transfer. So very interesting. Thank you again. So the next, I invite Professor Li issue the certificate for keynote speaker. So invite Professor Huang Zhongwei, Professor Peng, Professor Lu, and Professor Wang Jin, and so. So that's all for this morning's speech. So we will continue our conference at 2 p.m. So thank you. Enjoy the lunch. Thank you.
这个是。
Professor Liu and I will chair this session. It's a great pleasure to host this keynote session of this conference. To begin, please join me in welcoming Professor Zhang Dongzhu from Anhui University of Science and Technology, who will deliver a keynote speech titled Research Progress of the World Jet at Anhui University of Science and Technology. Professor Zhang has specially interested Associate Professor Wang Yan, also from Anhui University of Science and Technology, to present their work on health. Let's give him a warm round of applause. Professor Wang, please.
尊敬的各位专家、各位前辈，我受张东素老师的委托，我来代表我们学校做我们团队的这个高压水射流研究进展这么一个报告。我是来自安徽理工大学的王岩。我就是因为这是一个我们整个团队所做的工作，我从以下5个方面做这个进展的汇报。第一个呢是 磨料纯水射流和磨料水射流协同自净钻孔的这么一个研究。第二个呢是高压泡沫射流胀裂破岩这么一个技术的研究。第三个呢是磨料水射流切割乌基材料的一个研究。第四个是100兆帕前混合磨料射流装置的这个研究。第5个呢是磨料水射流切割矿用锚索装备的一个研究。 这是第一个，是我们开展的纯水射流、磨料水射流符合自净钻孔的这么一个装置的研究。它的基本原理是这样子的。因为我们之前呢，我们现有的研究呢，多数是自净钻孔的时候，就是用于自净的这一部分射流和用于钻孔的这一部分射流，多数是同一种，要么是同样用纯水，要么同样是用磨料水射流。我们想着是否可以尝试 在前方用于自净的这么一部分射流，我们采用磨料水射流，这样呢可以利用磨料水射流实现这个比较高效的破岩钻孔。然后自净的反喷自净的这一部分射流，我们采用纯水射流实现。它呢有一个优势，就是我们用于反推自净的这一部分纯水射流呢，它没有磨料，这一部分没有磨料，可以 在实现反喷自净的同时，可以有助于排除这个前面的煤岩的这个碎屑。这是一个装置的基本的这个原理图啊。这边右侧的右侧的这一部分，上部呢是我们的这个一个同轴的复合管道，它用于实现就是纯水射流和磨料水射流的这个同轴的这个输入。 下方的右侧下方的这个图呢，是中间它有一部分省略一部分，那是自净的管道，同轴管道这一部分我们省略掉了。下面呢是钻头部分，钻头部分前半部分是一个单个的一个磨料水射流的一个磨料水射流的一个带加权元件的这么一个用于钻孔的这么一个部分，后部分呢是4个均部的纯水射流的反喷，就是反向推进的。 下面呢左下侧的图呢，是我们用于就是开展前期预研的一些选型的，我们选了不同直径的这个磨料射流的喷嘴和不同直径的这个就是纯水射流的喷嘴，用于前期的验证。为了完成这个就是装置的设计呢，我们首先开展了这个数值模拟，就是确定这个比较好的这个或者是优化的这个喷嘴结构。 开展的数值模拟分析呢，当前向喷嘴为2.5毫米，它的充实的这个就是可冲孔的直径大概能够达到40毫米， 能够实现我们这个就是能够覆盖掉装置的最大的这个外径，能够实现它的这个就是整个机构的前进。后部分呢，我们做了多组的这个就是仿真，最后呢，我们取的是1.5毫米的这个自进喷嘴4个均部啊，然后实现后向的这个喷嘴自进。最后呢，就是确定的结构参数组合是前向喷嘴2.5毫米，后向喷嘴是1.5毫米乘4。接下来呢，我们做了这个搭建了整个这个平台的这个系统，对这个装置进行了这个是一个初步的实验。系统主要包括前面的这一部分呢是用于产生模料水射流的系统，后面中间这一部分呢是一个31.5兆帕200升的200升每分钟的这么一个泵啊。再往左边呢，右上角部分呢是我们做的煤岩的试样，是泡沫混凝土和那个煤粉是1:1的。下侧呢是我们做的一个简易的一个测自进力，就是我们为了验证它能否测自进力的这么一个装置啊。我们开展了这个就是自进的这么一个实验。这里呢简单放一个结构原理图吧，或者是一个动画，示意一下原理啊。纯水射流经过2部分，一个泵供纯水射流向前2部分，一部分呢是输向外侧同轴装置的外侧啊，用于反喷自进。另外一路水呢经过模料混合装置，然后呢可以实现直接输向前向喷嘴钻孔自进。最后呢，我们就是开展了这个在模拟的这个煤岩上面呢，我们做了这个就是一个实验啊，声音听不到啊。最后呢，我们大致的就是根据这个初步的实验结果，我们就是根据实验结果呢，我们看了一下，在2.5毫米的前向喷嘴，它的成孔就是钻孔的直径是45毫米，然后呢，钻孔效率比较高，同时呢，这个后向的1.5乘4的这4个喷嘴能够实现这个装置的自进，也就是说，整个实验呢初步验证了我们的这个设计的合理性啊，实验呢也验证的这个整个方案是可行的。后期呢，我们会再接着进一步的完善这个实验，想着把它能够实现我们预定的5米的这么一个自进的距离。接下来第2部分呢是就是这个高压泡沫射流这个破岩的这么一个技术的研究。这个因为岩石的这个抗拉的这个强度远低于其抗压的强度，所以我们尝试用这个高压泡沫去把岩石给它胀裂，这样实现破岩。这个整个装置上半部分呢是这一部分呢是这个模料的是那个泡沫的存储装置，中间这一部分呢是释放，然后下面部分是密封装置。它基本的工作原理是这样子的。我们呢首先呢在这个岩石上钻孔以后，将装置推入这个预钻的这个孔中，之后密封，然后这个就是接着是释放泡沫接着是释放泡沫，最后呢这个高压泡沫瞬间被释放在这个孔洞中，然后岩石被破碎。高压泡沫的胀裂的这个我们也有一个这个实验的情况在孔深为140毫米，孔的直径是50毫米，泡沫压力16.5兆帕的这么一个条件下，高压泡沫冲击这个钻孔时岩石的裂纹首先扩展至表面，之后呢这个裂纹网络贯通高压泡沫，使岩石扩展成这么一个小的这样一个的小的碎块。同时呢，这个泡沫它可以覆盖在场地周围一定程度上降低了就是这个破碎现场的它的粉尘的含量。接着呢，我们实验研究了孔深、封深密度、泡沫压力、泡沫质量对岩石的破坏效果的影响，建立起了这个岩石破坏的这个临界的参数模型。我们研究认为，高压泡沫射流冲孔，它在破碎的这个过程产生的这个冲击应力波，使钻孔的底部产生了应力集中现象，促使了裂纹的产生和岩石的破碎。研究表明，在我们给定的这个参数的射流压力下， 能够在岩石表面形成漏斗状的这个破碎坑，破碎的直径可以达到500毫米。通过改变胀裂参数可以实现岩石内部的这个宏观裂缝的产生，然后弱化岩石的强度。第3部分呢，是我尝试的将磨料水射流这种加工应用于这个，就是算一个探索吧。我们在探索用于加工聚变装置内部的一些特种材料。这里呢是一个托卡马克装置的一个简易的这一个结构示意图吧。聚变这就是受控核聚变这个领域呢，最近是一个风口，因为我在那个我博士和博士后所在的团队呢，我们做这个相关的研究，所以我就在想，我们当时呢内部装置的一些材料加工面临的一些问题，我们想着能不能用我们这个磨料水射流的手段，然后呢做一些探索吧。它大概的这个基本的或者说工作原理是这样的：这个等离子体内部等离子体，被挤压以后产生这个聚变反应，聚变反应释放出热量，然后下面的这个偏滤器，这个呢，它就类似于什么呢？类似于这个锅炉里面的这个，类似于这个高压锅炉烧开水的锅炉里面的它的一个往外排热量的这么一个导管，里面冲的是水，里面通水呢把热量引出来这是偏滤器。偏滤器呢，它呢直接承受这个高温等离子体的这个冲击，然后呢把热量给它沉积下来，然后引出。因为它的内部的这个新闻联播上面前一阵子也放的这个等离子体内部的核心温度能够达到1亿度，然后呢，它的目前实现的是1042秒的这么一个连续的放电，实际上呢能够辐射到沉积到这个偏滤器表面的温度也会在1000度这么一个量级。也会在1000度这个量级，因为呢，所以呢，它就对这个偏滤器这个结构，它的材料和加工工艺提出了很严苛的要求，其中呢，这个钨基材料包括纯钨、钾掺杂钨、碳化锆钨等一系列钨基材料是这个就是偏滤器上面的面向等离子材料的最有潜力的这些材料我们做了一个这个研究的尝试，下面的这幅图。就是右下侧的这个图呢，是慢走丝线切割所切出来的式样，它的这个微观表面，从那个气泡状的结构，那个是热影响区域，而这种热影响区域对于偏滤器这个结构，是影响它的寿命的，这是第一个。接着呢，我们看另外一个，我们所做的下侧这一部分，这是我们用水射流切割的式样，这里能够明显看到是没有热影响区域的。这个这一点是，所以可以说是这个研究中所能够取得的第一个有意义的点吧。这里呢，我们对这个切割式样也做了一个简单的我们做了前混的切割，前混合磨料水射流的切割，做了后混合磨料水射流的切割，取了一个典型的式样。这个式样本身呢，它与磨料水射流切割这个硬脆金属材料，它的宏观形貌是一致的。上部是光滑区，下部是粗糙区。然后呢，如果这个不做这个射流角度的控制的话，它会有这个切割的残余从它的去除的这个表面来说，上部呢以离削作用为主，然后下部我们取了3个，按照不同的深度依次加深的取了3个。深度方向上的这个式样对应的这个小的 A、B、C 这3个式样，可以发现，随着这个切割深度的增加，它的这个去除的这个表面的微观形貌变得不规则，是与宏观形貌是能对应的。然后呢，主要的去除呢，上部是以这个磨削、离削为主，下部则变成了这个材料的脆性断裂。为了就是从理论上去提供一些验证我们的这个分析的，就是我们对这个微观形貌的这个分析结果，我们做了一些仿真。这里的仿真呢，主要就是去测量这个磨料水射流它的磨料粒子的速度变化的这么一个趋势可以发现，就是这里呢作用过之后呢，随着这个作用深度的增加，磨料水射流粒子的速度呢是逐渐减弱，最后 归近于零，然后产生溅射。至于我们目前磨料水射流在切割方面所做出的这个比较权威的研究结论是一致的，就是说，随着这个切割深度的增加，能量耗散，然后磨料粒子运动变得不规则，以至于使这个切面从上部到下部，它的这个作用的这个去除作用的典型方式发生了变化。另外呢，从上部到下部，从光滑到粗糙这么一个区域的变化趋势也是一致的。这里呢是两组典型的，这几组典型的磨料水射流这个切割式样的它的宏观形貌和微观形貌的对比。从这儿呢实际上是比较明显的，能够看出这个切割就是它这个充实去除作用呢，这个它的形式发生的变化。同样呢，对于这个就是从宏观形貌上来说，如何去去除这些加工缺陷，目前呢我们也没有什么好的办法，只是说去理论验证了这种加工方式是可行的。所以如果这个各位专家如果有做这方面研究的，可以给我们提供一些帮助，我们都交流一下。材料的排号，刚才讲的是钾掺杂物，它的排号是 KW-270，就是这么一个，它是这个排号的材料呢是通用的，是能查到的。接着，因为偏滤器的它的表面是要耐受高能粒子的冲击，受到高能粒子的冲击呢，这种冲击就是它的冲击作用会使这个偏滤器，就是我们的切割表面或者是材料的切割表面呢，会产生这个皲裂作用，而这种皲裂作用到达一定程度以后，然后偏滤器就会发生失效。所以呢，为了验证我们这种加工工艺它是能否提高就是材料加工表面耐受高能粒子冲击的能力，我们做了电子束打击实验。这个呢是在中科院做的实验，这呢是一个电子束枪，然后现在是开着的状态，工作状态是要关闭抽真空的。然后呢，中间的这个是我们的这个试样，我们这是两组实验我们都做了，做了这个慢走丝线切割的切割式样的表面的电子束打击实验，也做了磨料水射流切割的式样表面的这个打击实验。主要呢打击的这个主要参数热负荷是20兆瓦每平米，然后呢我们按照打击时间1秒、2秒、4秒、10秒。间隔时间呢不同，间隔时间有1秒、2秒，以及20秒。我们在4×4平方毫米的范围内做打击测试，它中间每次打击呢是有时间间隔的，它是要有一个冷却时间的我们做重复打击实验。最后呢，打击实验的这个就是图片有很多，我找了2个典型的最具代表性的同样的是2秒的打击时间，同样的参数，2秒的打击时间，20秒的间隔，打击30次以后，上部的这个线切割式样，它的表面形貌发生了明显的这个就是我们说叫起泡、皲裂这种情况。我可以再给各位专家翻一下前面的这页报告。这里右下方那个图面是没有经过电子束打击的慢走丝线切割的式样的照片。接着这一幅呢，就是图片四幅图片中的这个左上角这个呢，是经过就是2秒20次，2秒间隔2秒打击时间间隔20秒，然后30次循环的打击后的然后下面的这个实验，正下方的这个实验是我们用水射流切割实验的，同样的打击次数以后，可以发现磨料水射流这个切面的它的这个式样呢，就是明显的没有发生，就是很明显的它的性能就是保持得很好，原貌保持得很好，就是它的耐受高能粒子冲击的能力要优于这个慢走丝线切割。这个点呢，是我们可能是这个小点研究中所取得的第2个很有意义的。这个呢，我们想用这种方式来证明，像那个中科院那边给他提，像证明我们这种加工方式从性能上能够提高装置的这个某一方面的参数，某一方面的性能参数。至于这个4秒间隔40秒打击这个30次以后，这个发生的这个变化就更明显了。水射流的那个实际上呢，发生的这个变化就变化趋势也很小。第3个呢是 我们做的100兆帕的这个前混合模料水射流装备的研发。这里我们做了这个100兆帕的这个相当于这个模料混合罐吧，其中呢这个主要的参数15升，然后呢这个流量15升，然后呢它的容积是20升，100兆帕，用的是这个喷嘴，我们做实验的喷嘴0.8毫米80目的16砂，使用这个16时的。其中呢，这个喉管结构呢，它的结构参数、它的长径比，对于这个模料粒子的混合，或者是我们用得率这个词来进行衡量的话呢，这个是它其中的一个关键部件。我们做了一些这个尝试，这里呢是做的一个模拟，就是做的这个数值模拟。数值模拟呢是想看一下这个不同的喉管的尺寸，它在这个就是不同的这个工作状态下对于混沙效果的一个影响。之后呢，我们又对于基于这个前面的不同参数的喉管的直径的这个影响呢，我们又尝试对它做参数的优化。这种参数的优化呢，最后呢，我们就是最后确定了这个最优的参数值。这一部分的详细的这个研究呢，后面明天有那个我们团队的谢怀北老师，他会做详细的展示，我这里就不做过多的讲解。这里呢是用这个，我们用这个图像灰度化处理以后呢，对图像灰度进行二质化处理以后呢，就是取不同的截面看这个模料粒子混合的情况。这里呢，就是最后呢，是我们发现，在喉管直径14毫米，喉管长度12毫米，进料口直径10毫米，这个喉管出口与下料口距离为7毫米的这么一个条件下，它的这个就是得率，也就是模料粒子的混合率效率能够达到这个34.4%这个数值，去衡量的话还是比较好的。第5个呢是模料水射流切割这个矿用锚索的这么它的一个装备的研究我们这个呢是一个企业合作的，是这样的，这个前混合模料水射流呢，它的装置呢相对来说要轻一点，便携，能够运到矿井下，所以呢，我们基于前混合的装备基于前混合模料射流开发这个装备，而前混合模料水射流呢，目前单罐不可避免的是装沙，我们想的是探究一下如何因为我们为了降低工艺辅助时间，我们探究的想呢，如何在单罐模料，我们寻求一个最优参数，能够实现就是最大数量的这个锚索的切割这是关于那个单根锚索，这里我们建立了单根锚索它的这个模料切割的用量与这个不同工艺参数的这个比值，做了一些这个切割实验。因为呢，锚索呢，它是一个空间曲面结构，为了就是分析一下它这个有切割残留，为了如何这个消除这个残留呢，接着呢，我们做了这个切割路径的这么切割的这个一个仿真然后呢，为了探究这个更好的这个切割路径，接下来呢，基于这个仿真的结果，我们尝试了3种，就是 A、B、C 3种这个路径的这么一个切割。第一个呢是直线，第2个是圆弧，第3个是倾斜的这么一个切割实验。最后呢发现呢，就是这个路径 A 就是直线的这个是切割残留效率就残留最少的基于这个切割路径，接着呢我们又进行了切割工艺参数，包括射流的压力、径给的速度模料的浓度等等这一系列的这个工艺参数的这么一个优化最后呢，我们建立了这个就是基于最优路径的基础上，我们探究了一个可以说是比较优化的这么一个射流结构参数，然后呢实现了这个就是把这个工艺参数给它定下来最后呢，我们联合这个企业开发了这么一个模料水射流的这么一个煤矿井下锚索切割装置，这里是在企业的那个车间拍的，它比较凌乱。这个标称是40兆帕200升设计的目标是单班200根8个小时工作制，我们这个目前的这个设计参数都能够达到 就是都已经实验验证了，能够达到。接着呢，就是我们这个也取了证了，对，和企业联合也取了这个那个安标的证了，对。好，我报告就是这些，谢谢大家。
Thank you very much for your nice presentation. So we have 5 minutes, so I think we may have one short session, and then I will give up a second for Professor Wang. Is any question from I
我想问一个问题呢，就是那个前混模量射流，我看你是中间是吧？一个管线过去那个砂管，它的那个砂比能控制吗？
可以。
可以到什么样的精度？比方说我要6%、8%的体积比，或者20%，这些控能调吗？
可调的范围，目前我们能实现的在20%多到接近30%这么一个质量比的范围内。对，谢谢王老师。
Thank you, and one more short question. So I have a short question. I think the foam jet, the mechanism of foam jet is quite different with pure water jet or abrasive water jet.
Foam jet.
In controlling of your foam jet, what's the main parameter to control the rate of the machine object? The main parameter. Also control the area of rate of
the diameter of the rocket.
Yeah, foam jet.
Foam jet.
What's the main control parameter?
I'm sorry.
那你怎么控制那个这个尺寸的打击的范围？
we can control the progress. Yeah.
Okay, thank you. Thank you very much for that. And nice presentation. So this is the presentation for keynote speaker. Next, please join me in welcoming Dr. Chen Jinpeng, Principal Expert of China National Machinery Industry Corporation, and the Hebei General Machinery Research Institute Corporation Limited, who will deliver a keynote speech about the development of China water technology stands the key to the integration of technology products and markets. I please Dr.
好，尊敬的各位专业领域的前辈啊，刘老师，尊敬的各位专家各位同学还有各位同仁，下午好啊。 我是那个合肥通用机械应用陈正文，很荣幸呢有这次机会呢向大家汇报一下我们国家的那个水射流技术领域的标准化工作啊。本人呢从事水射流高压泵和水射流技术工作呢30多年来呢，主要从事产品的研究、产品开发工作。那其中重要的一项工作呢就是标准化工作。那么我将从5个部分呢进行汇报。那么首先呢，浏览一下我们标准化工作的那个概况吧。这个标准对标准的理解呢，实际上它的内涵呢有6个含义。这个标准呢，本质上呢，它事实上是一种约束，是一种那个技术规范、技术规则也技术要求。那么标准呢，它制定的原则呢是协商一致性，因为标准呢，它要去追求社会的秩序和效益的最大化。那么它要有公开、公平、公正，所以呢，它的制定的过程呢，相对要规范化，形成规范化的文件。那么标准这个产生的基础呢，是科学、技术还有经验的那个综合成果。那么标准最后呢，形成的是一种它的特点呢，是一种共用的和重复使用的文件。那么我们国家的标准呢，主要分那个政府主导的标准和那个市场主导的标准。政府主导的标准呢，主要由那个国家标准和那个行业标准，还有地方标准。而国家标准里面呢，又有强制性国家标准和那个推进性国家标准。那行业标准和那个地方标准都是推进性的标准。那个市场主导标准呢，主要由团体标准和企业标准。那么团体标准呢，也是近几年标准化改革来后出现了新生事物，也是这几年兴起来的。那么我们国家的标准化组织开始水射流这个领域标准化工作呢，要追溯到上个世纪呢90年代，1991年我们就开始组建这个喷射设备那个标准化技术委员会的筹建阶段，一直到96年呢批复了当时的叫机械工业喷射设备标准化技术委员会。那个喷射设备标准化技术委员会这个被政府批复的成立呢，就意味着我们这个行业得到了政府的认可，就是标志这个行业呢正式的确立它的行业地位。这个标委会呢，到2009年呢升格成全国喷射设备标准化技术委员会。今年2025年呢，我们已经是第4届换届了。那么全国喷射设备标准化技术委员会呢，主要负责呢高压水射流设备、喷涂机、喷砂机，还有射流泵和喷射器以及工业喷嘴领域的标准化工作。其中呢有一个工业喷嘴呢领域的工作呢，由我们下面的一个工业喷嘴分会负责。这个分会的领导人呢，也就是我们黄仲伟教授。那个标委会建立之初呢，我们就构建了这个领域的标准体系框架图。那么我们高压水射流设备呢，在我们这个喷射设备的体系，这属于首要地位。再就是高压水射流设备，下面分了清洗机、切割机和那个专用水射流设备以及水射流附件这几个产品领域。那么经过几十年的那个发展呢，我们国家的那个水射流技术领域呢，已经建立了完整的体系，有基础标准，包括那个名词术语和那个喷嘴试验方法，还有安全标准，就是高压水射流作业安全规范，还有那个小型高压清洗机的那个安全规范。然后产品标准呢，从高压水切割机、清洗机，一直到成套的机场跑道除胶设备，还有高压水射流床铺除锈设备，还有大罐清洗设备，以及系列的喷嘴系列的产品标准，也就建立了完整的体系吧。然后从这个标准体系上来看呢，这个我们国家是唯一在世界上各国家建立了完整的这个水射流标准体系的国家。单就这个从这个标准研究的角度来看呢，我们国家还是处于领先地位的。那个我们国家的产品标准呢，已经覆盖了我们高压水射流的所有的参数范围，从那个低压的1兆帕的这个大罐清洗，小低压力大流量的清洗，一直到超高压的500兆帕、600兆帕的小流量的超高压水切割机，中间的每一段呢都有对应的产品，是小型清洗机、高压清洗机和那个床铺除锈设备等等。也就是说，从梳理我们的这个标准这个体系呢，你就看到可以展示了我们国家的水射流技术的那个基本的应用的这个技术应用现状。 那么下面呢，我就简单介绍一下从这个几个标准这个发展历程来看。首先呢是那个通用的水射流设备的标准的发展这样概况。那么从我们这个超高压水射流技术研究最初的那个联系目标呢，它是想找到一种新的那个切割工艺。但这个水射流技术真正在工程上首次应用呢，市场化应用呢，它是反而是从这个高压清洗机这工业清洗应用领域开始的。那么上个世纪80、90年代的清洗机呢，就在我们国家逐步兴起，开发出来进入市场。当时呢，我们及时的从87年就制定了第一部的那个往复式高压清洗机的一个技术要求。到95年呢，又制定了这个标准的那个形式参数和试验方法。99年的这个标准修订，一直到2020年的最新版的那个高压清洗机，历经了这个过程呢，实际上这个过程呢也从参数上展示了从最早的200兆帕到现在的这个参数300兆帕，机组功率从最早的那个250千瓦到现在的800千瓦。它从这个标准的发展脉络呢，也看出了我们产品的那个向大循环的发展的脉络。小型清洗机呢，1992年的时候我们发布了第一部的那个高温清洗机，99年发布了那个微小型清洗机的那个行业标准。那么随着这个我们国家这个人民生活的改善呢，小型清洗机呢现在呢已经逐渐走进家用清洗机和商用清洗机呢不断市场。所以呢这个时候呢这个市场又受到重视呢，我们在04年呢24年呢及时出版了小型高压清洗机的国家标准，全面的行业标准呢升格为国家标准。然后对超高压切割机这个标准发展呢，实际上我们2000年左右的时候呢，1998年呢，我们通用院开发了这个当年的全国的第一台超高压水切割机。到2000年左右呢，这个产品呢逐渐开始被市场接受，所以呢，2002年呢及时的发布了超高压水切割机的行业标准。经过几年的发展呢，10年升格为国家标准，然后18年呢就再次修订了。然后在这个超高压水切割机产品发展过程中呢，又派生了2个典型的这个细分领域的产品，那就是以那个深海水射流切割装备的移动式水切割机，移动洗车也及时出布了这叫移动切割机标准。它这个呢主要应对这个现场在线切割的。然后呢中间呢还有一个派生产品呢，就是细分的机器人水切割机标准。然后在基础标准方面呢，这个名词术语呢，我们是2015年就发布了这个喷射设备分类名词术语的那个行业标准。经过几年的市场检验呢，以后到2022年呢升格为国家标准，就喷射设备名词术语。然后基础标准的试验方法标准到25年才发布了第一部的那个水射流喷嘴试验方法的标准。那安全标准呢，事实上从1997年，当时那个80、90年代水射流高压清洗在中国广泛的应用，为了应对那个市场的需要呢，发布了高压水射流清洗作业安全规范的行业标准。10年呢，这个标准升格为国家标准。25年呢，因为这个水射流附件技术的发展呢，还有一些作业工况的变化呢，我们又对这个标准及时了修订。那个在这个最前面的捋了一下我们这个标准的大概的发展，这个通用设备的标准历程。在这个通用这个产品标准的制定过程中呢，我们水射流设备标准呢形成了2大特色的一个条款，就区别于其他机械产品的条款。因为我们一般的机械产品的标准的内容呢，都包括那个基本形式和基本参数，还有那个技术要求。试验方法、检验规则等等，这些要素呢是所有的产品标准要素。但是对我们那个水射流设备标准呢，我们增加了一个要素叫结构的组成。这也是我们水射流产品的特色。我们水射流产品呢都是一种综合的小型的成套产品。那么我们规定我们水射流设备呢有高压水射流发生设备，有泵机组，也就是还有呢这个管路系统，也就是高压水的输送系统，还有那个喷枪，包括控制系统，这呈现了我们水射流产品的基本的这个4要素。这个4要素的这个组成构成元素呢，构成了我们这个后续的所有的水射流产品标准的一个要素。 还有一个基本的是我们这个创新的理念呢，就是一个治病指标理念呢，就是也是我们这个产品的特色的，就是我们叫初始工况，也就是我们水受流设备的那个初始工作点的工况。那么它的具体含义呢，我们是规定的，就是当我们这个高压水受流设备初始工作的时候，泵的流量全部转化为这个射流的流量的时候呢，我们系统的压力呢，应该在90%和105%那个额定压力之间。也就是说，我们的这个初始的压力不能低于额定压力设置压力不能下降10%以上，也就是，然后或者呢是在额定工作压力下，那你的这个流量，也就是泵的流量90%呢要转化为射流流量，或者也就是说呢，就是这个液流法等的液流流量呢不能超过这个系统那个泵的产生流量的10%。这两个这个初始工况之间的核心要义呢，就是说压力，因为我们知道高压水压力是我们这个受流作业能力的那个保证。那么压力的下降呢，我们允许在工程上允许的下降幅度呢，也就是说根据设计工程需要呢，允许误差呢是10%，所以我们规定不能下降10%。那个两个90%的这个理念流量压力或者什么样呢，它是呢实际上对应了这个泵的机组的产生的功率转化为射流功率的转化率，也就是不能低于90%。这一个约定指标呢，就基本上定义了那个性能的参数的这个性能指标。然后这个指标，这个初始工况的理念呢，也贯穿了我们这个水受流设备的这个使用始终。那么我们水受流所有的设备呢，都要规定那个可靠性指标。可靠性指标核心的呢，就是易损件的寿命指标。那易损件的寿命指标，我们怎么判断？比方喷嘴，我们什么样的怎么样说是这个喷嘴已经失效了呢？它的判定依据呢，就是说，在喷嘴喷射期间，其他的情况在跟周期条件不变的情况下，当你的系统的压力下降超过10%以上呢，那么说我们这个喷嘴呢就说明判废了，已经磨损了。同样的，这个网封、密封这些密封泄漏，也就是我们在其他的工况条件不变的情况下，这个因为网封密封泄漏带来了你系统的压力下降10%以上，也就是我们这个密封的寿命呢就已经判废了。也就是说，初始工况那个2%概念呢，这也是我们水受技术产品标准的一个基本的技术要求的理念贯穿其中。那么我们超高压水切割机呢，主要是两类主流产品，一个是传统的那个我们传统意义上的是后混木料水受流技术为代表的那个切割机。这一类的切割机呢，主要是用于切割和加工，所以呢，我们对切割精度呢比较重视，所以规定了切割精度在这个最低的要求呢是加减0.1毫米。而对于那个移动式水切割机，也就是移动式水切割机呢，它主要是用于那个在线现场破拆切割作业、强行救援，这个危险场合的破拆作业。它这种切割机呢，它更强调的呢是这个切割速度，它对切缝质量没什么要求。所以这个标准呢，它主要规定了这个不同功率的机组的不同最低的那个切割速度，它的考核呢是以4毫米的钢板呢作为统一的考核对象，这样呢它就便于那个设备的那个检验和考测。那讲这两个意思呢，就是说我们对不同的产品的标准制定呢，我们都有侧重点，都要使这个指标呢可信，既能满足市场需要的应用的需要，又便于我们的检测和评价。这就是基本标准、产品标准的这个基本要求。然后安全作业规范标准呢，我们是主要规定了这个人员的培训，从人员的培训开始，一直到那个作业前的准备工作和那个作业过程中的作业规程，一些那个注意事项，以及作业后的对设备的维护保养的这个注意事项等等。这个安全作业规范呢，是现在已经成为我们高压水受流现场作业的一个培训的这个基本的教材。安全规范的出现呢，可以说是极大的推动了我们市场。因为这个高压水受流作业呢，实际上它是带有一定的危险性的。在初始推广的时候呢，因为这个没有标准，这个企业应用的时候呢，它就存在了安全风险。那你有了标准以后呢，它在管理上呢就有了合规性的依据、法律依据。所以呢，这样呢它就敢于用这个工艺，用这个工艺呢，它也有依据。这个是安全规范的。 然后，我们水射流这个名词术语呢，主要是包括在我们喷射设备名词术语的前一部分，这里专门的章节。我们对这个水射流的这个形式和结构参数，还有水射流装备的一些部件等等，也是常用的一些部件呢，都进行了规定。名词术语的规定呢，就是我们这个用词呢标准名称呢是规范化，这样呢便于我们的那个商业啊和那个技术的交流和沟通。那么下面呢，我就介绍一下这个专用设备，也就是专用生产设备的这个技术这个产品标准。我们水射流，这个技术啊，从通用的水切割机、清洗机到专用的水射流设备呢，实际上是我们的一个产品进步的标志，也是一个呢，这类典型的产品呢有，其实机场跑道除胶设备，这个大型曲面构件的。5轴联动的超高压水切割装备，这个成套装备，这个呢是应对那个航空辅材料构件的这个机翼切割的，然后超高压水射流，床铺除锈设备、大型厨罐清洗设备，一直到现在我们正在要制定的那个道路标志线的水射流清除设备和那个自动洗车机。那么我们说水射流为什么说从通用到专用是一个进步呢？我们讲。一个所谓颠覆性的技术呢，我们水射流技术从任何的一个领域一直到专用化出现呢，它往往呢是标志一种新的工艺的产生。那么就它会淘汰以往的这个工艺。从这个意义上讲呢，它说它是颠覆性技术呢，是也一点不夸张。那么我这里典型的案例呢，就是超高压水射流床铺除锈设备。超高压水射流床铺除锈，超高压水射流除锈工艺的出现呢，以后这个彻底淘汰了传统的这个除砂工艺。关于这部分的内容呢，我们后面因为有一个专报告来介绍这个技术它的背景啊意义呢，这里就不说了。但是我从标准的角度来看一看，我们对于这一类的设备定位的设备标准是怎么制定的。我们首先讲这个标准的那个组成部分呢，这个描述很简单，但事实上呢，构成定义这个有怎么样描述它，为列哪些内容，实际上是有深刻的含义的。我这里呢是解析一下。你看，我们把那个水射流这个除锈设备呢，我们把真空回收设备要列入它的那个除锈成套设备的必要组成部分。那为什么？因为这样讲呢？因为水流真空回收系统要保持这个除锈产生的污水都能回收利用，这样呢保证了作业环境的清洁，符合那个绿色发展的理念。然后我们的这个执行工具，我们这列举了爬壁机器人、屋底作业车、大壁作业车，而我们没有把这个现在正在用的这个高空作业车上加操作的那个平面清洗器的作业呢，我们不把它列入它的必要的组成部分的，那个不推荐。这个呢是引导，就标准引导性，也就是说，我们认为这个标准引导呀，这个机器人是这个技术发展的这个必然趋势发展，智能化发展呢代表了这个设备的这个发展方向。所以从这个简单构成这几个要素呢，我们就标准的所谓的引导作用，这个推荐中在技术的引导中呢，也就在这些理念中。然后这个技术参数的这个决定，我们没有把那个160千瓦以下的那个机组列入了我们除锈设备的参数，就是因为在这个机组功率太小呢，它失去了工业应用的价值。而压力呢，我们是最低，实际上现在就最高的。只规定了300兆瓦，因为在过高的压力呢，带来设备这个可靠性的降低，技术呢也不太成熟，这个压力等级呢已经满足了我们目前的工业的需要，所以参数的制定呢，它也有很多的讲究的。然后在这个技术那个性能指标上呢，我们对各个工艺机组的那个规定了它的最基本的那个最低的这个清洗除锈速度的指标的要求。那么除锈速度，因为我们这个作业对象呢，以前的形状不一样，最后会不会的达到各种的等级不一样，那所以有不同的对速度。但是我们只对那个典型的代表的要求的2.5节的这个作业效果，对这个情况下的作业速度做了规定，这样呢便于我们标准的那个可操作性。然后呢，这个对这些标准的那个规定的一些技术内容， 比方说作业效率，这个作业效率怎么检测，我们都有的详细的方法规定。那么我们把这个作业前的那么原貌的形状的图片，选出了几种典型的图片，作业后的一个等级各个等级达到的效果都形成了图谱，这样呢便于大家这个执行这个标准的检验判断指标。因为对这种东西，这个作业效果的这个判断呢就。然后高压水射流清洗这个超高压水射流清洗这个规范这个标准的出现呢，实际上同时呢也促进了我们这个储秀技术工艺呢从这个向其他工业领域推广。那你比方说我们现在这个超高压储秀设备呢已经推广应用到那个大型储罐的表面储秀这个工艺，因为大型储罐呢实际上跟我们船舶呢也存在同样的问题，它们只不过是短时作业对污染呢。管得稍微松，因为它就一个罐子干2天，它就换了地方了，不像那个。但是呢，它这个新的工艺、环保的工艺出现呢，它也是一个必然要被大家都采用的。那么有规范的标准出现呢，这个它促进了它的这个宣传吧，就是应用。那第4部分呢，我想呢介绍一下我们这个水射流技术。标准咨询应用过程呢，现在面临的一些难题，也就是我们的一个方向。首先呢，上面我们也提到的，就是说那个高压水射流作业呢，这个工程化应用的关键技术的部分呢，它有2个部分，一个是关键是水射流的产生，也就是低压水一直到高压水喷嘴喷出来这个产生这部分。从高压水射流这水的产生部分呢，我们那个理论研究呢，基本上还是归我们工程用的。第2个部分呢，就是射流出来以后。到作用到那个我们作业对象是这个，也就是我们真正的作业效果，这个地方的理论解析，就是上那个鲁教授的标准讲的，也提到了这个问题。实际上他就是研究这个方面的问题，就是说我们怎么样水射流的参数和我们作业的这个效果，这个比方说我们现在前面讲的作业效率，怎么样用这种理论解析的方法，能不能推导出来它的速度什么东西？这样有了理论解析呢，我们就能。我们现在的所谓的效果呢，都是靠检验、试验得出来的，它毕竟有一定的局限性，数据那个离散性比较差。但是呢，如果有在理论上分析出最佳的那个效率，那么说我们现在标准是规定了最低的要求，那它最后的最佳工况在哪里？最佳效果在哪里？最佳的功效在哪里呢？我们不知道，这样呢，我们做这个设备的能效评价分级呢就做不了，就不好把它分成能效1级、2级、3级能效分级。还有一个关键的技术呢，就是超高压这个射流的检测技术。那么像黄老师也讲了，我们可能测500米的音速的呢还可以测量，实际上就是这种测量也技术呢还不好普及应用。那么对于这个250兆帕以上的2倍马赫数的那个超音速射流呢，现在就没办法流产，没办法测量它的打击力，也就打击应力，就是单位面积打击力，总打击力可以测，单位面积打击力应力呢也不能测。那这个不能测呢，我们就不好规定那个这个射流产生的最终的效果，就没有一个评价的指标出来，这样呢妨碍了我们这个能效等级评价的。也就是我们这个设备产生多少效果的评价呢也没有，因此呢，这个我们可以讲呢，高压水射流呢，有很多的优点，就是无污染，这个粉尘污染，对在7个应用上呢，对7个材料的无选择性，尤其在一些易燃易爆的那个危险的环境呢，它已经是无可替代的。但是毫不隐晦的讲呢，我们的能效呢相对来说偏低，所以呢。既需要呢我们的能效评价方法，还有呢需要我们开展这个高效的这个新型的射流，比方说空化射流，还有那个脉动射流这一类的射流的工程化应用技术的要增早应用，否则的话呢，它这个能耗呢将制约我们这个水射流的技术的推广应用。好，第二现在遇到难题呢是智能化水射流装备的这个标准的制定的指标制定，那么智能化呢？是所有到机械作业到自动化作业的是 历程。那么智能化以机器人为代表的话，所以呢也刚做。那么等级和那个水射流作业效果等等的那个指标怎么确定呢？现在还是一个难题。虽然我们已经启动了这个计划，但是我们这个困难呢，我还没解决。好，最后那个我们总结一下，我们搞水射流就有5点。我们搞水射流呢，搞技术研究，我们最终的目标呢，还是要把这个技术呢应用到市场上，在市场上推广应用。那么这个从技术到产品到市场的推广呢，我们标准在这种中间呢是不可或缺。我们技术这个成熟度要9阶，那么我们有了标准的出现呢，是这个第9阶，也就是产品市场化的一个标志之一。那个标准的工作呢，又是以科学技术研究为基础的，所以呢，我们希望大家的科研工作者呢，就是我们水射流行业的这些老师们呢，就积极的投入到我们标准的技术工作中去，尤其对于我们现在讲到遇到的那个能效评价分级、超高速射流的测试方法、测试技术，还有一些智能化射流这个产品的那个指标的制定的这些，需要大家呢共性的智慧。那最后呢，我这个最后一点呢，也就是说。反复就强调一下，就是我们呢希望呢我们的科技工作者呢不要把我们的不要整天搞高大上的，我们的标准工作呢虽然很基础，但是也很重要。大家为我们的这个行业呢贡献自己的智慧和力量。那么我们这个里呢要关注标准化工作呢，你要关注一下呢国家标准化委员会的那个2个网站，在这个网站上呢，所有的标准的发布和列项等等的标准的信息呢都是公开的。那好，我的汇报呢完毕，谢谢各位。有什么要谢谢批评指正。
Let's give us again our round of applause. I think we still have 5 minutes, so maybe Dr. Chen give us a real understanding of the importance of standard, and we understand that it's very important to promote the development of technology. So I think promoting maybe shortly we have only 5 minutes. I'm going to even in Chinese. Okay, I want to ask one short question. So,
那个不好意思，抱歉，我那个中文英文水平还是听不太懂。对。
我知道标准很重要，但是这个你像现在这个标准，最新标准是我看的是2025年是吧？
对。
这个标准制定以后到市场里面要市场来执行，也要按照规范。那么这中间要经过多长时间的我们这个考察期，还是说马上要执行？
标准呢，它发布以后，一般的5到6个月就是可以执行了。它是在这个，你这个黄老师讲的这个意思的，我知道这个意思。你就是标准刚发，实际上所以标准制定的过程中呢，实际上是一般来说呢，对我们比较成熟的技术，在市场经过考验的一个技术呢，才能制定标准。但是如果你要超前制定标准呢，也是要确保这个技术标准制定的技术指标什么东西的符合实际现状。在标准执行过程中呢，还会出现一些比方说有一次可能知觉不周到的地方，这个时候呢，我们会根据这个标准执行过程中呢，它是及时的修订。基本上原则上呢，我们这个标准呢，5年必须要修订，5年修订。
执行以后执行的要
对修订，它是根据这个技术和使用情况出现的问题，不断的修订它的内容。所以标准那个产生了修订了以后，直到这个技术落后了，这个标准没人用了，然后再把这个标准作废。
Thank you very much for your as presentation. Here is presentation for the keynote speaker. Next, please join me in welcoming Professor Liu Hualing from China University of Petroleum Institute, China. He will give us the keynote speech titled Advancement of Downhole Intensify Development to penetration for
Thank you, Session Chair. So it's my pleasure to give a presentation here. First, I'd like to pay my respect to Professor Liu Benli, who is the important representative in water jet technology. 向刘本利老师致敬，他是我们的前辈。Second, I'd like to deliver a warm welcome to all aspects, industrial partners and guests and friends from Japan. So I'm Hualing Liao from China University of Petroleum, which is located in Qingdao in Shandong Province. The title of my presentation is Advancement of Downhole Intensified Development to Improve Rate of Penetration for Deep Drilling. So this work was supported by MINS Paris in France and the Geostar Industry Company in France and the Imperial College of London. So this work is an international cooperation. So I'd like to give the contents from three aspects. First, about the working principles and the novel concept about downhole intensifier and the latest progress in downhole intensifier development and lab tests on complete intensifier and Mount Harmon and lastly Kangaroo. So first, I'd like to give a brief introduction about ultra high pressure jet assisted drilling. Just now, Professor Chen gave the standard how to define the ultra high pressure water jet. If the output pressure is higher than 100 megapascal, that's the ultra high water jet. So how to improve the output pressure for downhole intensifier? So this technology is used ultra high pressure water jet and pressurize only a small part, drilling fluid to ultra high pressure flow to help and improve gel cutter braking efficiency. They incorporated with the conventional lock braking and cutting cleaning. So this technology can substantially improve rate of penetration. So from this, from this map we can know, so water jets of water flow or drilling fluid flow can be divided into two flow. One is conventional, another one is ultra high pressure water jet. So after a survey of state of art, the intensifier can be categorized into two groups. One is utilizing drilling fluid for pressurizing. Another one is utilizing axial vibration and energy of jet stream, because during drilling, due to water rotation and the revolution of jet stream, so how to convert mechanical vibration into hydraulic energy. So there are two categories for downhole intensifier. So from this map, we can see drilling fluid, when drilling fluid passes through the intensifier, only 5 or to 10% of drilling fluid could be pressurized to ultra high pressure degree. Then the remaining 19 to 95% of drilling fluid is also just like flow through conventional passage than for available cleaning. So this is the flow chart, flow routing of the drilling fluid. So after we consider the conventional water jet action on drilling, so there are maybe water jet play 4 aspects role in assisting improve rate of penetration, just like reduce tool temperature, mechanical loading, alternating stress, and which effect of for cutter and clean will able to prevent recursion and mitigate chip hold down effect. And last, for assisting breaking to prolong tool lifespan. So this is some pictures for explain how ultra high pressure water jet to help improve drilling gel bit cutter breaking efficiency. This is our traditional point of view. But after we consider, we put forward another, or we call it a novel concept. So water jet, maybe after, if we can create a circular slotting at the bottom of the hole, maybe which can release the local stress, just like we call the in situ stress, to reduce the local stress like this, so we can improve the general leak breaking efficiency after circular grooving. So based on this idea, so we conduct some research work, just like numerical simulation, to check how much the loading efficiency could be reduced. So from this map, we can see that during the normal drilling, so there's stress concentration at the failure area. So this area, due to the higher stress, so we increase the log strength. So it's hard for gel cutter to break. So after if we can create a circular grooving, so the local stress just below the gel bit could be reduced. So after the simulation, we found that even the radial stress, hoop stress, and the effective stress could be reduced up to 50% to 8%. So also we conducted some lab tests from single cutter impact and cutting. So from this map, we can see that when the circular grooving increase, the breaking volume increase in portion 2 grooving depths. So we can find that the debris size or the debris size increase also. So that means after a circular grooving, the locking breaking efficiency could be increased. So this demonstrates our idea. Also, we conduct single cutter cutting here. So on the confining pressure, we find that if there's a circle grooving, the fluctuation of cutting force will be decreased. Also, the debris from the cutting also increase. That means breaking efficiency is increased from the cutting force and from the size of the debris. So based on this simulation and lab test, we changed or we modified the installation of ultra high pressure nozzle. So before, we install ultra high pressure nozzle near the center of the bit to improve the cleaning efficiency. But after after previous introduction, we modified the location of the ultra high pressure pressure nozzle at the outside of the gel bit. This maybe we can create a larger circle grooving. So this is the magic box metric body pre-DC bit. Another one we call the steel body. So in China, we manufacture this type of gel bit, PDC bit. So in your European partner, they manufacture and design this type of PDC bit. So second, I'd like to introduce the latest progress in downhole intensified development. So till now, we have developed 3 types of downhole intensifier based on the knowledge energy we use. So we divided into them in 3 types. First, we call it driven by positive downhole motor. So another one is utilize the gel stream vibration energy. So the last one is we developed it in this recent year. We controlled pressurizing process and resetting process by electromagnetic valve. So also we manufactured the prototypes for these 3 types of intensifier. So also I'd like to give a brief introduction about the working principle of these downhole intensifiers. So first, type of intensifier driven by positive displacement motor. So this type of intensifier utilizes the energy of hydraulic motor as power in downhole drilling situation. That means convert the rotational movement of hydraulic motor into reciprocating movement of piston pump. Through this type of spatial spiral cant reverse mechanism. So that means convert rotational movement to reciprocating movement for pressurizing chamber. So another one we called downhole intensifier utilizing gel stream vibration. Just as we know, during drilling, especially in deep and ultra deep drilling, gel stream vibration is serious. So can we utilize this type of vibration energy? So based on this idea, so we develop and design this type of intensifier. So that means during the downward movement, we call axial vibration. So we can use this mechanical energy to pressurize drilling fluid, and the drilling upward. So the drilling fluid, a small part of drilling fluid is absorbed into the pressure chamber. So based on this downward and upward movement, part of drilling fluid inside a gel stream could be pressurized. So this is the working principle of downhole intensifier utilizing vibration energy. So we analyze the piston development, maybe velocity and output pressure with the gel stream performance. So another one may be a little complex. So for the intensifier controlled by electromagnetic valve. So I just showed a flash video. So this type of intensifier utilizes the basic working principle of pump. That's based on the close section area of piston. That means the large close section area with the low section area, and also depending on pressure difference between larger end and the small end. So also that means utilize the pressure difference and the piston area difference. When we control the resetting process, so from previous 2 types of intensifier, we find that we control the resetting process by motor movement and gel stream vibration. But here, we control the resetting process by electromagnetic valve. So we can control the duration, control the duration time. So from the simulation or theoretical analysis, we find that the output pressure feature is different. So for the pressure driven by PDM, which is the the pressure wave is a triangular wave. For the output pressure feature generated by the intensifier utilizing vibration energy, this is sine valve. But for the intensifier controlled by the EM valve, we find this we can get a square valve, that's longer duration of output pressure. That means we can get an entire circular grooving at the bottom of the hole. So this type of wave that we need for grooving or for slot cutting. So I'd like to show the entire research process. First generation, in fact, is simple, and we conduct in order to check our idea for the intensifier. So we use electromagnetic valve and hand together to check the output pressure features. So from this video, we can find, oh, this idea is checked. Then we manufacture. So we find at the beginning, for the first type of intensifier, first generation, the pressure is just like 2 times compared with the input pressure. So after this, we manufacture the first, second generation. We call the single pressurizing chamber intensifier controlled by EM valve. So the pressure ratio is 1 to 8.5. That means if we set 1 megapar for input pressure, we can get 8.2012 megapar for output pressure. So also the stroke of pressure is half meter. So that means we can get a longer duration. So the pressurizing volume of water jet is only about 0.3 liters per second. So this is the measurement we get from the lab. So we find that if we can set, when we can set the pressurizing process and the resetting process by timer. So if we set 10 seconds for pressurizing and 10 seconds for resetting process. So when the inlet pressure is set to 14.5 megapar, we can get more than 112 megapar. The real pressure ratio is about 7.72. And the duration time is about 2 seconds. That means every rotation of drill bit, we can get an entire circular groove. So in order to increase the pressurizing volume, also we design a double pressurizing chamber intensifier. So that means we use the same structure parameters. The unique difference is we use 2 pressurizing chamber. We hope 2 pressurizing chamber can work together. That means we can get a double output pressurizing volume. But we failed. This is the pressurizing test process during the lab. So when we use double pressurizing chamber, when the input pressure set to 20 to 25 megapar, we get a maximum output pressure 155 megapar. So maybe in laboratory measurement, this is the highest output pressure for downhole intensifier. But also just now I mentioned, we failed to get a double pressurizing volume due to the piston friction resistance or machining coaxiality in both pressurizing chambers. So it's hard or it's difficult for both chambers to operate simultaneously. So we can only just get the double pressurizing chamber, but is sequentially, not work together simultaneously. So So for these three types of downhole intensifier, only the downhole intensifier utilizing geosteam vibration has been tested in oil field. So in the year before last year, we test this type of intensifier in Talim oil field in the triaxic grow based formation at a depth about 4,000 meters. So the average rate of penetration is about 3.50 meter per hour. And compared with the adjacent section and adjacent well, we find less improvement for rate of penetration like 63% and 25% higher than in same formation. So at last, I'd like to introduce the lab test on coupling of downhole intensifier and mud hammer. So also this idea, we find that for ultra high pressure water jet, it's a little hard to cut for slotting or for cutting. So we put forward or propose the idea, can we make advantage of impacting action and jet gluing together. So the idea about this technology is maybe ultra high pressure water jet can make a slotting at the bottom of the hull to release the local stress to reduce the local strength. Then combining with the mechanical impact, maybe this impact can increase the water weight effect for high pressure water jet for cutting. So the coupling of jet and the mechanical impact may promote each other, achieving the goal of the increasing rate of penetration for both technology. So after a detailed discussion, we put intensify above of the mud hammer, so we can take advantage of this both technology together. So we conduct lab tests at the drilling bench of Mines of Palace at the Pau city in France. So this is the testing devices in Mines of Palace. So these devices can simulate downhole pressure up to 50 megapascal. That means simulate drilling condition at the 5,000 meter conditions. So from the lab test, we find that if the hammer and the water jet work together, the rate of penetration is double than the use hammer alone. So after we manufacture the intensifier and the mud hammer, we like to combine them together. So this is the connection between intensifier and the mud hammer. So that's O-ring will be used for O-ring ring for sealing and connect the intensifier and the mud hammer. So we use a fixed tube to connect the output of the intensifier and the mud hammer. Then we conduct a lab test. Here we connect from these connections. We use the gel bit with the ultra high pressure nozzle at the outside of beer bit, and mud hammer is installed just above the gel bit. Then the intensifier and the motor in the lab. So this is, I remember that. So this is some pictures, I remember. Oh, 怎么这放不了呢? So, okay. So, okay. Here, we can see this is the ultra high pressure water jet pressurized by intensifier, because it's a little dangerous. So this, okay. Yes, this one. Ultra high pressure nozzle. And in fact, I remember. So this one. There's no ways. If we can clearly listen the impacting action on the log sample. And here we can clearly observe the circle grooving on sand. Maybe this is just a medial hard log. But in the granite, it's hard to create a circular grooving. But we can observe a crater, maybe about 1 centimeter in depth. So in fixed impacting. So from this test, also we compare the normal drilling and the coupled drilling of intensifier and the mud hammer. From the test curve, we find that the rate of penetration with the coupling intensifier and the mud hammer is 2.3 times than the conventional one. So there's some pictures after the test. So this picture, one of professors from the Greece, he posted this picture to his friend circle and said, European cannot do without China, and the world cannot live from China. That's very interesting. So that's all for the downhole intensifier introduction. So last part is about conclusion. The first point about from the research work, we find that if we can create a circular grooving at the bottom of the hole, the reduction of effective stress can be up to 50 to 80%. Also, three types of downhole intensifier has been developed, and the intensifier controlled by electromagnetic valve have an advantage of adjustable jet frequency and longer duration for peak pressure, so which can improve efficiency of bottom hole cutting. And the field test show that intensifier could improve rate of penetration at real downhole situation. And the last one, the coupling of system of downhole intensifier and the mud hammer forms a synergistic log braking effect. So lab tests show a good performance compared with the conventional drilling method. So that's all. And at last, I'd like to express our thanks to the support of National Key Research and Development Program and EU Horizon Program. So that's all. Thank you.
Thank you very much for your nice presentation and the interesting work. I think we have 5 minutes, so we may have a short question. Any question from us? So I think it's very interesting. You show us that by intensifying the work efficiency will be improved about 30%.
Yes.
To 26 to 39%. So how about the cost? For example,
Cost, you mean? Yes, okay. A very good question. So till now, we haven't evaluated the cost experience. In fact, it's a complex systems, especially for downhole intensifier. That's a high requirement for stability, safety. So till now, we just conduct lab tests. But for downhole intensifier utilizing the jet stream vibration, that means the cost of the manufacturer is the double for a conventional drilling tool for rate of penetration. But the effect, because this type of intensifier haven't negative effect. Maybe when it's failed, it is just like a drill coral in downhole situation. So that's why we just conduct field tests for this type of intensifier. For other two, I think the safety, there are higher risk in field tests. Thank you.
Thank you very much for your last presentation again. So, I would like to clarification for your last. Now we will have a short tea break. We take this time to unite and network with fellow participants. We kindly remind everyone to return to the conference hall by 14:20, so we can continue with the next session. Thank you very much for your attention.
Okay, welcome back to the conference. So let's continue our meeting. So due to Professor Lu Yiyu has individual events the Vice Chairman, Professor Huang, asked me to continue the host for the meeting. So next, I'd like to invite Professor Zheng Jiyao from Northern Western Polytechnical University and Lou Senggang Intelligent Technological Company. So his speech, the title of his speech is The AI Era and Our Mission, Integrating Physical-Based AI with Industry Software. So Professor Zheng, please.
Thank you, Chairman. Well, I'm making this presentation on behalf of Professor Zhang Shijing. He is too busy to make this trip. Well, some of you may know Professor Zhang and I have worked in the water jet industry for many years. And you might wonder why we picked this topic in this water jet conference. I will give you two reasons. The first one, we believe we are already in the AI era. We know, I believe everyone here uses AI almost every day, right? Preparing report, PPT, or doing analysis, doing research. We use it every day, and we also use it for writing software code. But we are using the general AI model for doing all of this. But for us, we work in the industry. Who will provide the AI But in this project, the method proposed is with a different approach. From the same physical system, we still have the mechanism. From the mechanism, we can come up with the basic solution. And then we have a lot of data we collect a lot of data from the physical system. And then the data, we go through a system we call DIKW. That stands for data, information, knowledge, and wisdom. So through this system, we have a model. And then through the AI perturbation, we can mix these two approaches together, come up with the final solution. This project is an ongoing project. It's not done yet, but it's something Professor Zhang and his student is actively working on. Okay, we talked about industry software. We need to know what is the challenges we are facing and what are our opportunities. Industry software have a late start in China. Because of that, we have insufficient accumulation of industrial knowledge and technology. Users tend to rely on imported products. For CAD, CAM, and CNC software, we know SolidWorks, we know CATIA, and we know Mastercam, and Fanuc CNC controller, and Siemens. All of these brands mainly occupy the market in China. And the user already get used to this product, especially for the large manufacturer. It's very hard for them to accept domestic software products. And another challenge is that we have a severe shortage of interdisciplinary talents. And another one, we have very limited AI integration. This is also true for imported products because AI is so new. But that's also our opportunities. We know China government is actively pushing for technology self-sufficiency. So that give the domestic software developer a protected high-growth market. That's a very good thing. Second, China is the #1 manufacturer in the world. That means we have the largest laboratory for testing out our products. Third, AI plus is so hot today. Every industry is trying to get some AI components in their field, in their industry, and in their products. In fact, our team getting quite a lot of requests for develop this kind of industrial AI. And the last one is the Internet of Things. It's still a very key things in China, and China government is trying to use that to build industrial Internet of Things platforms. So all of this gives us a very good opportunity. It's the good time. Okay, our current research area, you know, Professor Zhang and I has worked in the water jet industry for many, many years. For now, we have not given up the water jet, but we have expanded our technology to a broader area. For CAM, we used to have CAM software for water jet. Now we expand from 2D to 3D. And for process, we expand from water jet to laser and other non-cutting process. And we used to develop 5-axis water jet machine. Now we expand to 6-axis industrial robot. And a key thing is we develop physics-informed AI. I will going to get to the detail. Okay, this slide I give you an overview of our 3D CAM software. This is AI-enhanced CAM platform for line form 2. Line form 2, that means the cutting tool looks like a line. That including laser, water jet, YEDM, and it can also extend to other forms of tool. And the full workflow for the 3D CAM is that we do a 3D path planning, and we generate G-code program, and we do a simulation. What are new in our CAM compared to our competitors? I talk about 3 here. The first one is automated surface selection. Let me show you a short video. This video shows we use this 3D CAM to do the program for this composite component used in the automobile industry. We use water jet to cut multiple holes in this part, but the multiple hole in this part actually is formed by a few thousand of small surface. For our CAM to do the automatic cutting path planning, we first need to identify the cutting surface. If you manually pick each cutting surface, that will take hours to complete a program. So we have this invention. We can automatically recognize the boundary of the surface, and then we do an intelligent grouping of all the cutting surface. And then we can generate independent path. And the second innovation is because we have a challenge for cutting impeller par using a water jet. Well, we know the impeller par, the surface is not a rule surface, but for water jet and laser, it can only cut rule surface. In Chinese, 直纹面. Water jet can only cut rule surface, but to do a programming on a free surface, on the impeller surface, there's no way to do it. Before, we have to have an engineer manually create two surfaces to enclose the free surface. But that's a very tough job and may not be optimized. So we developed our algorithm to generate mathematical model for the, you can see the two rule surface to enclose the free surface. That will greatly enhance the programming efficiency. The third one is 3D surface positioning. We can look at this part. This is very common in the automobile industry right now. It typically made out of carbon fiber. But this kind of part, there's no feature you can easily doing a positioning using a traditional tool, right? There's no position hole or edge. You can use the traditional tool to identify its position. So we invent a new method that we can do localized scanning of the, for example, for this part, we can scan this corner, scan this edge, and scan this edge. Just three localized features. And then we can match the, this cloud data with its model. Then we can do the finish, we can complete the position. Okay, and the key function of the software is it do a parametric machine modeling so that we can do a real 5-axis machine simulation. It do smart surface and curve recognition. It can automatically generate the two path and doing the optimization. And it also includes an AI-assisted process parameter. And it can do a full 5-axis simulation and detection. And let me give you a show of this. So for cutting this part, it required a 5-axis machine cutting with water jet. We can very quickly doing this program and doing a simulation to make sure the motion is correct. Otherwise, for 5-axis machine, it's very easy to crash. Okay, I will talk about another example, our smart cam used in the industry. We have extended our cam to a lot of area now. One of that is in the automobile manufacturing. This is a hemming process. Hemming in Chinese is 滚边，包边，把那个钣金2块钣金把它压合过来，形成这个边沿。It's called hemming. We can do offline programming and simulation, and we provide process intelligence and automation. And it have a data-driven monitoring and analysis. Well, one of the things I like to highlight is that this hemming process is not like a traditional hemming. Traditional hemming is that you just teach the industrial robot at every spot, so it gives a proper location and force to fold the metal. But this hemming process is the use force control device. So that means every spot you have a actively control force to make the folding. And our CAM can do the offline program. It also comes FEA process. From the FEA process, output the force at each spot, how much you need to use. You cannot calculate by hand. But FEA can do the simulation and give you the force. Then we can get the force from A and apply into a program. And then we have an automatic offline programming. And let me show you a short video. This just showing that there's no sound, but I just explained. It's just getting the data and doing a simulation, and you can also monitoring the actual force and the actual position. Well, this just gives you an idea. I won't get into detail of it. I want to show you another example of our smart cam. It's used in the picosecond laser micro machining using a 5-axis machine plus galvanometer scanner. So our CAM will do the offline program, not only the 5-axis machine, also the 2-axis galvanometer scanner. Combine the two together. And the workpiece is a contact lens. We need to make a dozen of this pocket on this semi-spherical surface. And it need to do multiple layers and different direction to do the laser etching to complete this part. And this is a CAM plus CNC. So we also make the CNC program. You can see the 3D machine. And also give you a short video. This is just the simulation of the cutting process. It first doing generating the cutting path, and then doing a machine simulation. This is a 5-axis machine. It combines AC turning table and with this galvanometer scanner. Okay, this is just give you an idea. Okay, now come to the process modeling. Some of you probably heard me talking about this before. This is something we have done for a long time. What this gives us right now for our future development is very important, because from this development, we know when we're doing this thing, we combine the physics of water jet cutting. We have a model of water jet cutting, right? And we combine with a lot of experimental data. But at that time, we don't have the AI machine learning method yet. So we use a multi-parameter regression method. But this gives us a very good experience to combine the physics and the data. We found this is very important. If you only use regression and you will take a lot of data, and when the prediction point is far away from your experimental point, the accuracy, it can be very, very wide. The error can be very large. But with the mathematical model, putting it together, you never have this kind of wild guess. You can have the error under control. And it's also extensible. When you're getting away from your experimental data, you can still get a rather reasonable prediction. So this is something we get from the experience and we use in our AI development. Okay, I have mentioned that we have expanded to laser cutting. And in laser cutting, we found this is a fiber laser, fiber optical laser. And it has totally almost 100 process parameters. Now, look at this table here on the left. This is the cutting parameter. It has over 20 parameters, like the power, frequency, the focus position, the nozzle size, all of this, over 20. And then when you're doing the penetration, usually it takes several stages of penetration. And on each stage, it has over 10 parameters. So just trying to imagine for a user try to do a new process, you have to set up all these parameters before you start doing the cutting. This is very time consuming, and then you have a lot of tuning time to adjust the parameters. Based on this, we do this thing. First off, we have a large, we have collect a large scale of data, and then we use the machine learning algorithm to develop the process model. And then we just one click, we can generate optimized parameter for all of this. So we believe this is it can enhance the efficiency. Okay, the third area we are working on is robotic accuracy. area. Why we are doing that? We found in the industry now, especially in the automobile industry, when you come to the shop floor, you can find hundreds of thousands of industrial robots are working. Not many people. But almost all of this robot is programmed by manually teaching. That means for doing a process, you have to manually guide the robot to a certain point and then record the position. And you do that 1,000 times. It will take several days to complete a program. It's very time consuming. So the ideal is that to use offline programming to replace manual programming. But when you do that, you find there is a gap between virtual and real. What is it? You have your 3D model of the robot and the workpiece and the fixture. However, the manufacturing errors of all these systems is quite different from your 3D model, right? I believe every one of you recognize that. And because of this gap, if you do an offline program, you find it's not correct. You still need to do a lot of manual tuning so that the efficiency is not that high. So that is a good reason why offline program is not used quite broadly. Well, to solve this problem, we bring AI to help. What we do, first of all, let me explain the PINN. PINN stands for Physics Informed Neural Network. The diagram on the right is the illustration of this PINN model. If you only use the neural network, then you only have the top part of it. You just have data, and then you use the neural network to come up with the prediction of the robot. But you will find, just like we learned from the water jet modeling, if you only rely on neural network, sometimes the error can be very large, and you require a very large number of data. But the PIN method, we put in the second component, is the kinematics of the robot. We have that. All of the robot, we have the kinematics. But in the past, not many people used that together with the data. But now we have the method to combine it together. You combine the formula with the experimental data to put together a model. And when you're doing this, we use a loss function to combine them together. And why this PIN is effective? The first one, it can constrain the solution. You no longer have a very wild guess from the pure data model. And the second one, it can enhance the data efficiency. Okay, I have to move fast. This is the test process. I will skip this part. And the result is that before the error correction, you can see this robot have up to like 14 millimeter in error. After the correction, it can reduce the error to under 1 millimeter. So it's quite effective. Our future research area is we try to develop a standardized PIN-based procedure for this kind of robot error compensation that can use on shop floor. And we also want to extend our process modeling by using the PIN method. And we want to expand our CAM for milling process. So that's our future research interest. Thank you for your attention.
So just now, Professor Zheng gave us a good introduction about the technology in another aspects from the AI with inductive software. So from his speech, I learned that the mainly inductive software focus on 3D CAM from the automated software surface selection, roller surface path creation, and 3D surface positioning, such as like 3D printer. Very interesting. So, are there any questions? So, may I ask two questions, short questions. First, in order to establish an AI model from the data, from information, knowledge, and wisdom, that means the most important is algorithm, AI algorithm. So, have we solved all aspects in this four from the data, information, knowledge, or wisdom? That means, have we found a solution to replace maybe foreign software, or have you developed our software at present time?
Well, for each particular problem, we have to focus on its unique problem, right? And the data, of course, will be unique to the process itself, and the mechanism will be unique. So all of this we have to develop, we have to get the mechanism, which is not easy to get a mechanism for the physical process. For the robot, the kinematics is relatively easy. But for other real process, getting a mechanism is not that easy. So this is something we will try to work on, but it will take a lot of efforts. I will call for more people to join this effort to develop industrial AI for our industry.
Thank you. Another question. We learned that Dr. Zhao is a key project from the National Science Foundation Committee. We know it's hard to get such financial support. Here, there are many dollars. So do you have any ideas or suggestions for application for such a project in water jet technology? Let's go on. So the last keynote speech, I'd like to invite Lu, Deputy General Manager Lu Hua from Nantong Coastal COSCO Shipping Shipyard Company. The title of his speech is The Application of Ultra-High-Pressure Water Jet Technology in Shipbuilding and Offshore Engineering. Please.
Good afternoon, everyone. My name is Lu Hua. I'm from Nantong. I don't know if you are familiar with Nantong or not. But recently, Nantong becomes quite famous because of the Jiangsu Football League. Unfortunately, we lost in the final match, but it's a strategic decision. My topic today, I want to present the research and application of ultra high pressure water jet technology in shipping industry and offshore industries. So we'll be divided 4 parts. First part is research background. So we are working from 2 industries. One called COSCO Nantong Shipyard is mainly for the shipping industries. We're going for repair jobs, and the COSCO Qidong, we are mainly for offshore new buildings. Offshore mainly for the building the project, offshore projects for oil and gas, offshore oil and gas field. You can see a picture from there. There are 2 pictures from Nantong Yard and 1 picture from Qidong. This is our project delivered because our Qidong yard was set up in 2008. Since 2008 until now, we're delivering a number of the offshore projects, including the drilling rigs, the deep water drilling rigs, and the wind farm installation vessels, and offshore projects, as well as the FPSO, floating production storage offshore offloading vessels. So we are both shipping and oil and gas industries. This is the topside module, a process module we built and delivered since 2009. So why am I here? Because we are working in these industries. Both industries, a lot of steel, carbon steels, a lot. You have steels, you're going to have a rust. So we need to remove the rust. The big amount of rust need to be removed. The traditional derusting method, initially from 1980s, we use mining ground derusting. There are chemical, they have a short blasting. Then we have abrasive blastings, mainly grit blastings. But this kind of traditional method, they have a lot of problems. The high labor intensive and high energy consumptions and high emissions. But most big problem is environmental pollution, a lot. When we work in the repair yard, every day is smog day. It's a cloud of dust when we do sandblasting and grit blasting in the yard. So we call. Another problem is we have a significant impact to the people's health. This is a big problem. We need to change. President Xi Jinping said, clean water, green mountain, a mountain of gold and silver. So we need to change otherwise we cannot survive. But ship repair market is quite a big market. China is a major ship repair and new building country in the world. We are taking about 2/3 of the global market. For the ship repair market, the workload will be about 30%. We call the steel, carbon steel surface treatment. It's a lot of work. You can see the pictures, as long as steels, you have rust. As long as you are sailing in the sea, there will be marine growth. This is why we need a brand new surface treatment method to replace traditional ones. So we studied many methods, but we eventually found most promising technology innovation is ultra high pressure water delasting technology. When we start to find solutions, we cannot find the right equipment. Since 1980s, the pressure of the water jet only 35 to 70 megapascal. Then in 1990s, to 150 and 200 megapascal. But even there's a supplier, an overseas supplier, American, Germany, UK, and even Singapore, they have a supplier. They can produce reliable equipment and produce high pressure, ultra high pressure equipment, but we cannot afford. This is a comparison between Germany, the world leading supplier, Germany equipment, Helsmann's, and the domestic technical levels. There's a big difference at times. So the reason why by 1990s and even 2000s, this kind of technology cannot be used in our industries because import equipment is too high, price is too high. Compare the price right now we manufacture equipment, only 1/3 of the cost compared with import equipment from foreign countries. Also, they have inadequate after-sales service. Also, spare parts, not only expensive, but have long lead times. We cannot wait for long times. Of course, there's also pollutions. The Western world, no treatment, the environment pollutions, even resources of waters. So there's a lot of problems we need to solve. A domestic supplier, we faced immature technology and short service times, and we don't have post-treatment technology at times. This is why we decide to buy ourselves. So we set up a research objective. We try to develop a complete set of technology with the proper rights by us with ultra water depth capacity equipment. With the enhanced design and manufacturing capability in China. With achieve engineering applications can be commercialized in these industries. Most important, we need to find a solution to pollution-free and zero or near zero emission. Eventually, we need to facilitate transformation, upgrading of domestic ship repair market, and achieve a sustainable delivery of these industries. We have to be survive. So second part about research technology. We set up research tasks. We divided 5 topics. Topic 1, research on surface treatment technology solutions. We investigate laser, we investigate add sand, add abrasive to the water, or add water to abrasive. Many kind of solutions we're trying to find. But eventually, it only can meet all our targets. The only solution is a pure water, high pressure water jet solutions. So topic 2, we need to develop the ultra high pressure water pump unit. This is the key equipment. The most critical one is a pump. and pumping unit. Third one is research on water recovery and treatment technology. Fourth, we need development of integration system, because the whole system need to work properly and work high efficiency. This is why for the number 5, because that time we don't have standard. We don't have standard of manufacturing, we don't have standard of safety, we don't have standard of procedures. This is why we need to set up the technical standard for this kind of a solution. So principle and theoretically is very simple. We use high pressure water, then we use with jet head or a spray head. Then we use carrying mechanism or carrying equipment. Then we need a post-treatment. This is why we need several components. Maybe we'll show the video, make a clear picture, which give you a short video. Otherwise, people cannot understand properly our industries. This is a floating dock. We put the vessel or put the ship on that. This is a pump unit. The spray head. They're rusty now. This is ice particle jetting. Yeah, just have you roughly picture about what. Sorry. So put the equipment to be commercialized in the industries, we need 4 categories, 4 criteria. Most important is reliability. We need to work stable, no breakdown. Second is safety, because operation with the safety. Third one is cost effective. Fourth one, we need to be environment friendly. That's why the 4 critical criteria we need to achieve. So this pump. Pump is, we have 2 types of the structure. One is vertical, one is horizontal. But vertical already is a patent of the Hellman's Germany company. So we use horizontal inline structure. So this is a liquid end, but technically we're not going to spend time on that because time is limited now. But critically for the pump, still there are several components. There's pressure-bearing components. Yeah, we use heat treatment technology and shrinking fitting technology and self-reinforcement treatment technology as a structural optimization and surface treatment. So because this is easy to crack, they made a lot of improvement on this in terms of materials, in terms of process. The second critical part is the sealing, lubrication sealing technology. We changed the material of sealing from packing to ultra higher molecular weight polyethylenes to polymer fibers. Also, we use kind of structure innovations. We use 2-stage high-pressure sealing plus 1-stage low-pressure sealing, plus cooling water circulation between high and low pressure. So the above structures, there's 2 types of the sealing. One is carrier sealings. One is packing sealings. We combine both. High-pressure stage, we use clearance sealing. Low pressure stage, we use packing sealings. We combine both, it works very good. Very stable. Another critical area is inlet and outlet valve assembly. Yep, we're not going to detail about that. When we develop the equipment, the products, we set up 2 stages. Stage 1, we develop the products with a high pressure jet pump unit, 280 megapascal, and a flow rate of 14 liters per minute. Because for this kind of the equipment, we are confident can be achieved. Eventually, within 1 year, we made it. It has been commercialized since 2020. It has been 5 years. Now widespread commercialized in this industry. Now step 2, we create the pump with 300 megapascal and 52 liters per minute. So this we compare the standard of German company, the same levels. So this kind of products, I mean, in this industry is top level in the world, compare the German equipment. But eventually made it. The prototype has been demonstrated complies all the design requirements. So now definitely the achievement is make significant milestone in this field. That's why I will work with Mr. Chen here. We are now leading the domestic position for this kind of equipment. Most important safety, because in the safety-wise, we also think a lot of methods, use a lot of reliable metal-to-metal contact seal forms, and drill hole to ensure no safety hazard when the seal failed. So we use safety rupture discs has been used, and the monitoring and control system has been used. We also set up a testing and verification platforms to evaluate all the prototype, the rusting performance, cost effectiveness, safety, as well as reliability. This is we call spray head or jetting head. to investigate the mechanism of intelligence and peace force from rotating. Also configuration for ultra high pressure water gradient. Also some hydrodynamic characteristics. So we don't go to detail, the time limit, okay. Optimize the metro designs. There's a process research and database development. The carrying equipment, because you have to carry the jetting head to the surface of the hull. They need robot, the wall adhesion, performance, and mobility. And also have load distribution innovations. Because it has been shown in the picture or shown in the presentation of Mr. Chen's. Again, for the online monitoring and research, established control of the entire operation process. And in terms of the post-treatment delivery technology, because we have the whole solutions, packed solutions, including the solid and liquid vacuum recovery. When we spray the water on the hull, we need to section back, we take it back. Because all the activity is to open space. We need a recovery of all this kind of the water, because including the waste water, including the rust, residue, including the painting particles. So also have a solid flow, multi-stage filtration and separation technology. Also wastewater reuse technology. And the solid waste, we do carbonization and the pyrolysis treatment technology. And also exhaust gas has been collected and purified. And environmental waste and noise has been monitored and controlled. This is a vacuum recovery unit. There's some studies, dynamic characteristic studies. This is waste post-treatment systems. This is multi-stage solid liquid separation. The water is cleaned. Water recovery rate exceeds 95%. So this system achieved a rotational rate of 90% of particular less than 10 megawatt in wastewater, and the wastewater reuse rate exceeding 90%. This is pyrolysis treatment technology. This is flue gas convert flue gas to puration integrated system. In terms of the moisture content, was only 0.844%. And noise we measured is 77.2. It's below the required limit, 90. So this integrated applications. In terms of standards, we developed 3 standards. The first one is national standard. Second one, in terms of the process standardization of this group standard. Third one, also group standard for safety. So we complete and has been approved by authorities. The 3 standard has been approved, has been issued in October 2024. Part 3 is project application. But currently, we have been delivering many equipment, in total more than 200 sets. For cost reductions, compared with other equipment, we have 30% less. For efficiency, working efficiency improved by 53%.
Sorry, a little quick.
Okay. So last one, conclusion and possibility. Anyway, we just say every coin have two sides. You have a lot of advantage, also have disadvantage. The first disadvantage, water jet cannot be used in the winter because low temperature, especially in north regions. And the second, cannot meet required surface roughness of steel plate. There's still the safety hazard because pressure too high, 3,000 megapascal. There's safety hazard. Also, there's rust recurrence problems. But another problem with the shortage, because increase the water from to the 3,000 megawatt, you need a lot of energy. So energy consumption is not economical. That's why we think ice particle can be the solutions. That we made it, that now it's halfway on the progress. This including the ice making and the ice mixing room temperature water, the robot, and also the jetting service, the last is we're working on now. Maybe also take some time to be commercialized. Yes, that's it. Thank you very much.
Okay, thank you, Mr. Wu. So from his speech, you know that the company focus on their research technology on how to improve processing capability and efficiency in the elastic industry. So their research technology work includes 5 aspects, including surface treatment and technology solution. Second, about the development of ultra-pressure equipment unit. And the third one, waste recovery and treatment. The fourth aspect, development of integrated system. And the last one about the technical standards. So covers the entire industrial chain. Thank you. So are there any questions? So, okay, I have a short question for you. So, have you made a comparison with foreign equipment or technology, such like just, or say, could you give us some important improvement of technical parameters, just like pump pressure, stability, continuous working time, and node performance?
Yeah, just say in the presentations we have, from beginning we have the standard, we have the German equipment as our standard. So German equipment in this sector is the top one in the world. That's why we set up a standard to reach, this is our target. Eventually we made it. The performance of the equipment sometimes is better than German equipment.
Good. So thank you. So that's all for today's plenary session. So it's a wonderful day. There are 9 keynote speech today. So we learn from this speech. So maybe we end today's meeting. So wish all of guests have a good night, wonderful and colorful night, and enjoy the dinner. Thank you. Any other questions from the secretary or from the organizing committee?